What if I told you that just beyond the edge of our Milky Way, there's a neighboring galaxy, close enough to study in detail, yet strange enough to challenge everything we think we know about the universe? A place where massive stars are born in cosmic storms, where ancient clusters drift silently through a distorted disk, and where a supernova once lit up the sky with a force that shook the foundations of modern astrophysics. This is not science fiction. It's real. And it's called the Large Magellanic Cloud. For centuries, it hovered in the southern sky like a ghostly smudge, dismissed as a mere curiosity. But today, it's at the center of some of the deepest questions in astronomy, from the origin of galaxies to the fate of the cosmos. In this video, we're going to journey deep into this mysterious galaxy, peel back its layers, uncover its violent past, and reveal how this small companion to the Milky Way might just hold the keys to understanding the universe itself. Let's begin. But before we continue, subscribe to the channel so you don't miss out on any of these videos. To understand the Large Magellanic Cloud, often abbreviated as LMC, we must first confront a truth about the scale of the cosmos. Our Milky Way galaxy contains hundreds of billions of stars, spanning about 100,000 light-years across. It's a vast, rotating spiral with its own structure, patterns, and mysteries. And yet, despite that unimaginable scale, the LMC, which orbits us like a kind of cosmic satellite, is so close in galactic terms that light from its stars takes only around 163,000 years to reach Earth. That might sound like a long time, but compared to the millions or even billions of light-years we measure for other galaxies, the LMC is practically next door. The LMC is a dwarf galaxy, but don't let that word fool you. In cosmic terms, dwarf is a relative term. With a diameter of roughly 14,000 light-years and between 10 and 30 billion stars, the LMC is a sprawling, ancient city of stars, nebulae, black holes, and dark matter. It's larger than many galaxies and more massive than most satellite galaxies of the Milky Way. In fact, for a long time, it was thought that the LMC was a mere satellite orbiting quietly around the Milky Way. But more recent studies suggest that the relationship is far more dynamic and chaotic, that the LMC may be on its first close pass around our galaxy and might even be distorting the Milky Way's own structure with its gravitational influence. In short, this is no passive partner. This is an intergalactic juggernaut. And the story of the LMC begins not in modern times, but in the deep time of human history, and far before even that, in the epoch of early galactic formation. When humans first began to observe the sky, the Large Magellanic Cloud was already visible to those living in the southern hemisphere. Ancient cultures in Africa, Oceania, and South America all recorded or described the LMC in their oral traditions or sky lore. But it wasn't until the age of exploration that the LMC was given its modern name. The famous Portuguese explorer Ferdinand Magellan, during his voyage around the world in the early 1500s, sailed under the skies of the southern hemisphere and took note of two cloudy smudges in the night sky, now called the Large and Small Magellanic Clouds. But make no mistake, these aren't just clouds of gas. The LMC is a fully formed galaxy in its own right, with all the complexity that implies. It's a barred spiral or irregular galaxy. Astronomers still debate its exact classification. It seems to be distorted, perhaps due to gravitational interactions with the Milky Way or the Small Magellanic Cloud, which is another dwarf galaxy nearby. These distortions have turned what might once have been a tidy spiral into a misshapen and asymmetrical swirl of stars. At the heart of the Large Magellanic Cloud are some of the most active star-forming regions in the known universe. The most famous of these is the Tarantula Nebula, also known as 30 Doradus, which is so massive and bright that if it were as close as the Orion Nebula is to Earth, it would cast shadows. Let that sink in. A nebula, a vast cloud of gas and dust, bright enough to cast shadows. The Tarantula Nebula is one of the most fertile star-forming factories known to science, and within its luminous folds lie some of the most massive stars ever discovered. We're talking about stars dozens or even hundreds of times the mass of the Sun, living brief, fiery lives before exploding in spectacular supernovae. In fact, one of the most studied supernovae in human history occurred in the Large Magellanic Cloud, SN 1987A, the closest supernova observed in over 400 years. When it detonated, it provided astronomers with a wealth of data, not just in visible light but across the electromagnetic spectrum, including neutrinos. This event helped solidify our understanding of stellar death and explosion mechanics. It's no exaggeration to say that SN 1987A revolutionized astrophysics in the late 20th century, and it happened right there, in our neighbor galaxy. But the LMC isn't just a pretty nebula or a host of massive stars. It's a cosmic laboratory. It allows us to study dark matter, stellar evolution, galactic dynamics, gravitational interactions, and even the expansion of the universe itself. Because of its relative proximity, it's a perfect testing ground for theories that would otherwise rely solely on models and distant observations. Its stars are close enough that we can study their individual properties, track their motions, measure their spectra, and learn their ages and compositions. We can see how galaxies interact with one another up close, how they merge, pull, twist, and collide. And those interactions are dramatic. The LMC is not static. It is moving, and it's pulling the Milky Way with it, slightly, but significantly. Its gravitational mass is so great that it's causing distortions in our galaxy's stellar halo, and even in the dark matter halo that surrounds the Milky Way. It's been proposed that the LMC could be responsible for observed anomalies in our galaxy's outer regions, and may even be reshaping the very trajectory of the Milky Way's future. There's also the Magellanic Stream, a ribbon of hydrogen gas trailing behind the LMC and the SMC, stretching hundreds of thousands of light-years across space. This stream is a relic of past gravitational interactions, a record of cosmic turbulence. It flows behind these galaxies like a galactic wake, and it may be feeding star formation in both the Milky Way and the clouds. And here's something even more staggering. While we used to think the LMC was a mere satellite of the Milky Way, some models suggest it may have been an independent galaxy until relatively recently in cosmic time. Some simulations indicate that the LMC entered the Milky Way's gravitational influence only a few billion years ago and might eventually merge with our galaxy in the far future. And when that happens, it won't just be absorbed quietly. That merger will create gravitational waves, trigger starbursts, and alter the balance of the Milky Way's dark matter halo. Speaking of dark matter, the LMC provides a unique testing environment for detecting and modeling this mysterious substance. Its motion through space, and especially its effect on nearby stars and gas, offers indirect evidence of its dark matter halo, a halo that may contain more mass than once believed. Recent studies even suggest that the LMC's dark matter halo could be about 10 times more massive than previously estimated, which would explain why it's had such a dramatic gravitational influence on the Milky Way. Let's also talk about the stellar populations of the LMC. Its stars are incredibly diverse. Some are young, hot, and massive. Others are ancient red giants, survivors from a long-gone era of the galaxy's evolution. The LMC offers a glimpse into the life cycle of stars across different epochs. Astronomers have mapped these stars using various surveys, including the OGLE, Optical Gravitational Lensing Experiment, and Gaia missions, to track their motions and map the structure of the galaxy in exquisite detail. The LMC also contains globular clusters, supernova remnants, X-ray binaries, and even potential black hole candidates. It has regions of intense radiation and complex magnetic fields. And it may even host planetary systems, yes, planets orbiting stars in another galaxy. Imagine that for a moment, alien worlds circling suns not in our own galaxy, but in a completely different one, visible as a tiny glowing cloud in the sky. The Large Magellanic Cloud is also important for one more reason: calibration. Because it is relatively close and its distance is well known, it serves as a key anchor point in measuring cosmic distances. This role makes it vital for establishing the cosmic distance ladder, the chain of measurements that allows astronomers to calculate how far away other galaxies are, and thus determine the expansion rate of the universe, the Hubble constant. Discrepancies in the measured values of the Hubble constant, known as the Hubble tension, may one day be resolved through better understanding of the LMC. It's almost paradoxical. Something that looks so small in the sky, a faint mist barely visible without a telescope, could hold the key to unlocking the largest scales of the cosmos. And we're only just beginning. To understand the internal complexity of the Large Magellanic Cloud, we need to delve deeper into its morphological structure, its gas dynamics, and its multi-wavelength portrait. The LMC doesn't present the clean, grand spiral arms that we associate with galaxies like our own. Instead, its structure is dominated by irregular patterns, asymmetrical arcs, and features that hint at tidal interactions. From afar, the LMC seems like a lopsided spiral, with one prominent bar-like structure running through its center and large segments of star-forming regions distributed unequally around it. This apparent bar isn't centered within the disk, and its off-kilter position has puzzled astronomers for decades. This irregularity could be due to past gravitational interactions with the Milky Way and the small Magellanic Cloud. When galaxies interact, especially if one is more massive than the other, tidal forces come into play. These gravitational pulls stretch and distort the smaller galaxy, warping its spiral arms, triggering bursts of star formation, and even dragging out massive trails of gas and stars. In the LMC, these tidal interactions may have played a role in sculpting its current form, particularly in creating the warped disk and offset bar. But what makes the LMC even more intriguing is that these features don't just appear in visible light. When astronomers observe the LMC across the electromagnetic spectrum, from radio waves to X-rays, an entirely new layer of understanding emerges. In radio wavelengths, vast reservoirs of neutral hydrogen are revealed. These gaseous reservoirs provide insight into how the LMC maintains its star-forming activity. Neutral hydrogen, HI, is the raw material for new stars. The LMC contains vast sheets and filaments of this gas, intricately structured and extending far beyond the main stellar disk. These HI structures tell a tale of ongoing inflow and outflow, some material streaming inward towards star-forming regions, and some being expelled outward, possibly due to supernova-driven winds or tidal stripping. In the infrared spectrum, space telescopes like Spitzer and Herschel have mapped out the dust content of the LMC. This dust, while only a fraction of the galaxy's mass, plays a critical role in shielding molecules from radiation, allowing stars to form in dense molecular clouds. Infrared observations reveal regions of intense warmth, indicating active stellar nurseries where massive stars are forming at a feverish pace. These hotbeds of activity are crucial to understanding how the galaxy continues to regenerate itself across cosmic time. But perhaps the most dramatic revelations come from ultraviolet and X-ray observations. These wavelengths expose the hottest, most energetic processes occurring in the galaxy, including young, massive stars emitting blistering radiation, as well as the aftermaths of violent supernovae. The Tarantula Nebula, which we mentioned earlier, is a prime example. It glows brightly in ultraviolet, revealing a cauldron of high-energy photons, shockwaves, and ionized gas. The LMC has been a prime target for the Chandra X-ray Observatory, which has uncovered dozens of supernova remnants, pulsars, and even high-mass X-ray binaries, systems where a black hole or neutron star is accreting matter from a companion star, emitting high-energy X-rays in the process. Each of these observations adds a layer of depth to our understanding. The LMC is not just a passive collection of stars, it's a living, breathing ecosystem of stellar birth and death. Stars are born in thick clouds of gas, ignite into nuclear fusion, radiate light for millions to billions of years, and then die, some in quiet fades, others in cataclysmic supernovae. These deaths enrich the interstellar medium with heavy elements, which in turn seed the next generation of stars. This cycle continues, and in the LMC, we can observe it in real time across the full spectrum of energy. But the LMC is also unique for another reason: it provides an intermediate bridge in galaxy evolution. It's larger and more massive than most satellite galaxies, but smaller than full-size spirals. That means it occupies a kind of transition zone, offering clues about how small galaxies grow into larger ones through mergers and accretion. Many galaxies in the early universe were likely LMC-like, rich in gas, irregular in shape, and forming stars at high rates. By studying the LMC in detail, astronomers are essentially looking back in time, peering into the kind of environment that may have dominated the cosmos during its early epochs. And then there's the dynamical future of the LMC. Recent data from the Hubble Space Telescope and Gaia mission have provided precise measurements of the LMC's motion through space. Surprisingly, it appears that the LMC is moving faster than previously thought. This suggests that it may not be gravitationally bound in a long-term orbit around the Milky Way, but instead is on a first-in-fall, plunging toward our galaxy for the first time. This changes everything about how we interpret its history and its future. If the LMC is indeed on a first-in-fall, then many of its current features, its distorted structure, active star formation, trailing gas stream, might be consequences of its recent encounter with the Milky Way's gravitational field. And its future is dramatic. Simulations suggest that the LMC could eventually merge with the Milky Way in about 1 to 2 billion years. This merger won't be a mere absorption. It will cause ripple effects throughout our galaxy, disturbing the stellar disk, sending gravitational waves through space, and potentially triggering new waves of star formation. But even more fascinating is how the LMC might affect the supermassive black hole at the center of the Milky Way. Known as Sagittarius A, this black hole is about 4 million times the mass of the Sun and currently lies relatively dormant. However, some researchers propose that the gravitational influence of the LMC, particularly its dark matter halo, could displace Sagittarius A from its central position or trigger renewed feeding activity, reigniting it into a more active phase. And this brings us to another incredible mystery: dark matter in the LMC. Though invisible, dark matter makes up most of the galaxy's mass. It doesn't emit, absorb, or reflect light, but it reveals itself through gravity. The motions of stars and gas in the LMC suggest that it is surrounded by a massive halo of dark matter. This halo may extend far beyond the visible boundaries of the galaxy, and its interaction with the Milky Way's own dark matter halo is a source of ongoing research. Some simulations even propose that the LMC's dark matter halo is reshaping the Milky Way's dark matter distribution, causing what some call a dark wake, a kind of gravitational ripple effect that alters the structure of the Milky Way itself. But perhaps most compelling of all is the LMC's potential to teach us about the formation of structure in the universe. Cosmological simulations, like those from the Illustrious and Ego projects, model how galaxies form from small clumps of dark matter, gas, and stars in the early universe. The LMC fits into these models as a textbook example of a satellite galaxy undergoing interaction and infall. It helps astronomers test these simulations, validate their assumptions, and refine our understanding of how the large-scale structure of the universe emerges from quantum fluctuations in the early cosmos. Even more profoundly, the LMC challenges us to reconsider our place in the universe. We often think of the Milky Way as the dominant actor in its neighborhood, a galactic colossus moving silently through space. But the LMC reminds us that the universe is dynamic, filled with motion, chaos, interaction, and evolution. It is not just a background object, it is a partner, a player, a potential disruptor in the future of our galaxy. And it is close enough that, with the right instruments, we can study it in a level of detail unthinkable for other galaxies. The more we look at the LMC, the more we realize that it is a microcosm of galactic processes, a reflection of universal dynamics on a smaller but still staggeringly complex scale. From ancient starlight to the birth of new suns, from quiet hydrogen clouds to explosive supernovae, from black hole binaries to dark matter halos, the LMC contains multitudes. And perhaps that is what makes it so irresistible. Because in the smudge of light barely visible in the southern sky lies an entire other world, a galaxy filled with its own history, drama, violence, and beauty. It is a story not of a single object, but of the cosmos itself, of how galaxies live, interact, and die. It is a story of matter and mystery, of gravity and light, of the known and the unknowable. And that story continues. As we press further into the complex anatomy of the Large Magellanic Cloud, the role of stellar populations becomes critical to our understanding. The stars within the LMC span a remarkable range of ages, from the faint, ancient stars that date back nearly to the dawn of the galaxy itself, to newborn stars formed in the last few million years. These varying stellar populations don't just provide a timeline for the galaxy's history. They actively map the rhythm of galactic evolution, encoding epochs of intense activity, quiescent periods, and events triggered by interactions with other galaxies. One of the most important tools in studying these populations is the color magnitude diagram, CMD, a kind of stellar fingerprint that reveals a population's age, temperature, and luminosity distribution. The LMC CMDs are rich with features: a clear main sequence, an evolved red giant branch, and populations of asymptotic giant branch (AGB) stars. The existence of numerous Cepheid variables in the LMC, pulsating stars with a known relationship between their period and luminosity, has also made the galaxy a cornerstone of the cosmic distance ladder. These Cepheids allow astronomers to calibrate distances with great accuracy, forming a bridge between local and extragalactic measurements, and anchoring the scale of the entire universe. But to truly grasp how the LMC evolved into what it is today, we must look at the chemical composition of its stars, what astronomers call metallicity. In astrophysical terms, metals are all elements heavier than hydrogen and helium. By analyzing the spectra of stars in the LMC, researchers can determine how enriched they are in these heavier elements. The trend is clear: older stars in the LMC have lower metallicities, meaning they formed from more primordial material, while younger stars show increased enrichment, having formed from gas that had already been processed through multiple generations of stars. This chemical gradient tells us not only about the LMC's star formation history but also about how it may have exchanged material with the surrounding intergalactic medium, and even with the Milky Way itself. Further complicating the picture is the evidence for stellar migration within the LMC. Unlike our own galaxy, which has a relatively ordered disk and halo, the LMC shows signs that stars can move across large distances within the galaxy, possibly due to gravitational interactions, past merger events, or the galaxy's own turbulent rotation. These migrations can blur the lines between population zones, mixing old and young stars in regions not typically associated with such variety. Perhaps nowhere is this more evident than in the Tarantula Nebula, also known as 30 Doradus. Though we've already explored its brilliance in earlier sections, it bears repeating how extreme this region truly is. It is not just the brightest star-forming region in the local group, it's a hyperactive stellar factory, so luminous and massive that it was once mistaken for a small galaxy itself. At its heart lies NGC 2070, a massive star cluster, and within that, the incredibly dense R136, a compact cluster containing some of the most massive stars ever observed. Some of these stars are more than 100 times the mass of the Sun and burn with blistering intensity, emitting powerful winds and radiation that sculpt the surrounding gas into twisted filaments and expanding bubbles. These stellar winds, along with shock waves from supernovae, contribute to what is known as feedback, the process by which newly formed stars influence the surrounding interstellar medium. In the LMC, feedback from clusters like R136 helps regulate star formation across the galaxy. By compressing gas clouds, it can trigger new star formation in nearby regions. But by dispersing and heating gas, it can also suppress future star formation locally. This delicate balance of triggering and suppression creates a mosaic of stellar evolution, where some regions bloom with activity while others lie dormant. And all of this activity takes place not in isolation, but within the broader context of the Magellanic System. This system includes the LMC, the small Magellanic Cloud, and the immense network of gas known as the Magellanic Stream. The stream is a sprawling ribbon of hydrogen gas that stretches over 600,000 light-years across the sky, a colossal reminder of the gravitational interplay between these galaxies and the Milky Way. Formed over billions of years, the stream likely originated from gas stripped out of the LMC and SMC by tidal forces and ram pressure stripping as they moved through the Milky Way's hot halo gas. The stream isn't just a relic of the past, it's an active part of the galactic environment. Some of the gas in the stream appears to be raining back down toward the Milky Way, potentially fueling future waves of star formation in our own galaxy. This makes the LMC not only a system of internal evolution, but also a galactic donor, feeding the ongoing life cycle of the larger universe around it. One of the unsolved mysteries of the Magellanic System is the origin of the leading arm, a structure of gas that appears to stream ahead of the LMC and SMC as they orbit the Milky Way. Its existence defies some models of orbital dynamics, and its metallicity suggests that it may include gas stripped not only from the Magellanic Clouds but also from the Milky Way itself. Some astronomers believe that interactions between the LMC's dark matter halo and that of the Milky Way are responsible for these bizarre features, illustrating once again how dark matter, the invisible backbone of galactic structure, continues to defy easy explanation. Delving further into this realm of the unknown, we find that the LMC has played a pivotal role in the search for dark matter and in the testing of alternative theories of gravity. The gravitational effects seen in the motions of stars and gas in the LMC cannot be accounted for by visible matter alone. Some researchers have used this data to test MOND, modified Newtonian dynamics, a theory that attempts to explain galactic rotation curves without invoking dark matter. While the LMC does not decisively rule in favor of or against MOND, it provides a valuable test case due to its irregular morphology, high gas content, and close proximity. Another cutting-edge area of research is the use of the LMC in the study of gravitational waves. While no gravitational wave events have yet been traced directly to sources in the LMC, it is expected that some of the compact binary systems within the LMC, such as neutron star pairs or black hole binaries, could be future sources of these ripples in spacetime. Advanced detectors like LIGO and Virgo continue to refine their sensitivity, and a confirmed gravitational wave event from the LMC would not only mark a historic moment in astrophysics, but also provide a new lens through which to study this remarkable galaxy. As we zoom out and place the LMC in the context of galactic archaeology and cosmology, its true value becomes even more apparent. Here we have a galaxy that is close enough to resolve individual stars, rich enough in structure to offer complex internal dynamics, and dynamically involved enough with other galaxies to act as a testbed for the theories of galactic formation, interaction, and evolution. It is, in effect, a natural laboratory available to us night after night, just beyond the reach of the naked eye but within the grasp of our telescopes and instruments. And for all its scientific significance, the LMC also holds a place of cultural and historical importance. For millennia, it has been visible to the peoples of the Southern Hemisphere, to indigenous Australian astronomers, Polynesian navigators, and ancient South American skywatchers. Its presence in the night sky is timeless, its glow a symbol of both mystery and familiarity. Ancient observers, lacking our scientific tools, still perceived its uniqueness, perhaps sensing on some level that this was no ordinary star cluster or patch of light, but something more profound. Even today, as we build ever more powerful telescopes, from the ground-based Vera C. Rubin Observatory to the space-faring James Webb, the LMC remains a prime target. Its proximity, complexity, and richness guarantee that it will continue to reveal new secrets with each new generation of technology. What lies within its deepest dust clouds? What still unseen black holes lurk in its stellar graveyards? What new physics might emerge from mapping its gravitational imprint on the Milky Way? We have come far in our exploration of this magnificent galaxy, and yet we have only begun to scratch the surface. Stars are the storytellers of any galaxy, and in the Large Magellanic Cloud, their tales stretch back billions of years, written in light, motion, and elemental traces. Among these countless narrators are the blue supergiants, glowing with the power of youth, their high mass driving fierce nuclear reactions that burn brightly but briefly. These massive stars often end their lives in supernovae, dramatic explosions that send shockwaves through their surroundings, injecting energy and heavy elements into the interstellar medium. The LMC, being rich in gas and dust, becomes a theater of continuous rebirth, where supernova remnants like N49 or the famous SN 1987A leave behind glowing shells of gas, neutron stars, or even black holes. These remnants are not just debris, they're sites of transformation, influencing star formation in nearby clouds and offering astronomers a glimpse into the death throes of stellar giants. Beyond the luminous and explosive, the LMC is also home to a vast population of low-mass stars, many of which are long-lived and quietly stable. These stars, especially the numerous red dwarfs, represent a kind of stellar immortality, living for tens to hundreds of billions of years. In their ancient glow, astronomers find a living record of the galaxy's earliest epochs. These stars, some more than 10 billion years old, formed when the galaxy itself was young and still coalescing. Their low metallicity suggests formation from nearly pristine hydrogen and helium, the basic ingredients left over from the Big Bang. Studying their composition and distribution allows scientists to trace the formation of the earliest galactic structures within the LMC. Among the more curious residents of the LMC are its stellar clusters, tight groups of stars formed from the same molecular cloud. The LMC contains thousands of these clusters, and they offer crucial insights into stellar evolution. Some of the most studied include the aforementioned R136 and also older globular clusters like NGC 1783 or NGC 1978. These older clusters act like celestial time capsules. By analyzing the stars within them, scientists can reconstruct the conditions under which they formed. Interestingly, the LMC's clusters don't all follow the same pattern seen in the Milky Way. Some show signs of multiple stellar populations within the same cluster, a phenomenon still not fully understood but one that could hint at complex formation histories or internal dynamics that recycle gas from multiple star-forming events. In its gaseous component, the LMC is particularly notable. Unlike many dwarf galaxies, which tend to be gas-poor due to interactions or internal blowouts, the LMC still retains a substantial reservoir of gas. This gas, primarily in the form of neutral hydrogen, is distributed in a somewhat irregular disk that's laced with tendrils of ionized regions and molecular clouds. The mapping of this gas, using radio and submillimeter wavelengths, has revealed spiral-like structures and filaments that suggest ongoing large-scale flows. These flows could be the result of the LMC's gravitational interaction with the Milky Way or even internal bar-driven dynamics. Such gas movements feed into regions of star formation, helping to regulate where and when new stars emerge. And not all gas in the LMC is visible in the traditional sense. Some of it is cold and dense, existing in the form of molecular clouds, which are the true birthplaces of stars. These clouds, primarily made of molecular hydrogen, H2, are often difficult to detect directly. Instead, astronomers rely on tracers like carbon monoxide, CO, which emit in the radio spectrum and serve as proxies for the presence of molecular hydrogen. Observations of these clouds in the LMC have revealed rich detail: dense knots where stars are forming, turbulent flows where magnetic fields and gravity wrestle for control, and expanding shells driven by previous stellar generations. The interplay of these elements paints a vivid picture of a galaxy in flux, caught in the continual cycle of birth, life, and death. The dust within the LMC is equally important. Though a relatively small fraction of its mass, interstellar dust plays an outsized role in galactic processes. Dust grains form in the cool atmospheres of aging stars and are spread through space by stellar winds and supernovae. In the LMC, this dust both reflects and absorbs light, altering the way astronomers perceive the galaxy. It also serves as a catalyst for molecular chemistry, helping to cool gas clouds and enable star formation. Observations by space-based infrared telescopes have revealed an intricate web of dust lanes, emission regions, and voids. These features don't just provide structure, they give clues about the timing and efficiency of past star formation, as well as about the galaxy's interaction with its surroundings. Surrounding all of this activity is the LMC's stellar halo, a diffuse population of stars that extends far beyond the bright central regions. This halo contains some of the oldest and most metal-poor stars in the galaxy, and it likely formed during the galaxy's earliest era of assembly. Interestingly, studies of the halo suggest it may contain stars stripped from satellite systems or acquired during past mergers. This raises questions about the LMC's history. Did it consume smaller dwarf galaxies in its youth? Is it still in the process of absorbing material from its environment? These questions touch on broader themes in galactic evolution and challenge our models of how dwarf galaxies grow and interact. The motion of the LMC through space is another vital element in its story. Using data from missions like Gaia and the Hubble Space Telescope, astronomers have been able to precisely measure the LMC's proper motion across the sky. What they've found is astonishing. The LMC is moving faster than previously believed, at speeds around 320 km per second relative to the Milky Way. This has major implications for the past and future dynamics of our galaxy. It suggests that the LMC might be on its first approach to the Milky Way rather than in a stable, repeated orbit. If true, this would redefine how we understand the gravitational influences exerted by and upon the LMC, and it would add fresh urgency to predictions about future galactic collisions. Indeed, the future of the LMC is intimately tied to that of the Milky Way. Models of gravitational interaction show that in a few billion years, the LMC will likely merge with the Milky Way, contributing its stars, gas, and dark matter to the larger galaxy. This merger will be a relatively gentle one compared to the upcoming Milky Way-Andromeda collision, but it will still leave a permanent mark. Simulations suggest that the influx of dark matter from the LMC alone could significantly alter the Milky Way's central mass concentration and might even perturb the orbits of stars and planetary systems in the galactic disk. In this way, the LMC becomes a kind of messenger from the future, a reminder that galactic structure is never static, and that even the most familiar cosmic landmarks are temporary. Observations of planetary nebulae in the LMC add yet another layer of complexity. These glowing shells of ionized gas, ejected by dying intermediate mass stars, are often used to trace both stellar evolution and chemical enrichment. In the LMC, planetary nebulae exhibit a range of morphologies and compositions, reflecting the diversity of their progenitor stars. Their chemical abundances, particularly of oxygen, nitrogen, and neon, help astronomers understand how stars contribute to the galactic ecosystem. Since the LMC has undergone different star formation histories and chemical enrichment processes than the Milky Way, studying its planetary nebulae offers a valuable point of comparison. Binary star systems in the LMC also provide crucial insights. These systems, where two stars orbit a common center of mass, allow for precise measurements of stellar masses, radii, and luminosities. Eclipsing binaries, in particular, are prized for their ability to yield direct distances, as the geometry of their orbits can be used to derive absolute brightness. These measurements are indispensable for refining our distance scale not just to the LMC, but to other galaxies as well. The LMC, thanks to its population of such binaries, remains a cornerstone for calibrating cosmic measurements. Among the LMC's binary star systems, some exhibit extreme characteristics that are particularly intriguing. These include systems with compact objects like white dwarfs, neutron stars, and even potential black holes. X-ray binaries, where a compact object accretes matter from a normal star, are especially luminous and provide a window into the end stages of stellar evolution. In the LMC, several such systems have been identified, each adding to our understanding of how binary evolution proceeds in different galactic environments. The metallicity of the LMC affects how stars lose mass through winds, which in turn influences how binaries evolve and whether they merge, form accretion disks, or collapse into exotic remnants. High-mass X-ray binaries in particular are more common in the LMC than in the Milky Way when adjusted for mass. This overabundance is thought to result from the LMC's recent bursts of star formation, which produce massive stars in abundance. Since these stars evolve quickly, they frequently end up in configurations that produce observable X-rays. Each of these systems serves as a natural laboratory for studying accretion physics, magnetic fields, and relativistic jets. Moreover, by tracking the spatial distribution of these systems, astronomers can map the history of recent star-forming regions in the galaxy. In the arena of gravitational waves, the LMC also becomes a subject of intense interest. The presence of binary black hole candidates and neutron star mergers in or near the LMC raises the possibility that this galaxy contributes detectable gravitational wave signals. While none have been definitively traced to the LMC as of yet, future observatories with greater sensitivity may be able to pinpoint gravitational wave sources in this relatively nearby galaxy. The unique star formation history and stellar population mix in the LMC make it a compelling target for such searches, potentially enhancing our understanding of how compact object binaries form and merge in different environments. Turning our attention to supernovae, The LMC's most famous example remains SN 1987A, the closest observed supernova since Kepler's supernova of 1604. When it exploded in February 1987, it sent a shock through the astronomical community and provided a rare opportunity to study a core-collapsed supernova in detail. Detected across the electromagnetic spectrum and even in neutrinos, SN 1987A became one of the most scrutinized stellar events in history. Its progenitor star, Sangelik 69 degrees 202, was a blue supergiant, an unusual choice for a supernova of this type. The explosion revealed new insights about how supernovae evolve, how shockwaves propagate, and how chemical elements are dispersed into space. Even decades later, SN 1987A remains under constant observation. The expanding debris continues to light up surrounding material, and the three-ring structure around it, likely shaped by stellar winds and mass loss before the explosion, offers a blueprint for interpreting the pre-supernova evolution of massive stars. The inner ring, in particular, has brightened over time as the shockwave slams into it, giving astronomers a front-row seat to a real-time interaction between supernova ejecta and circumstellar material. These observations have refined models of supernova physics and taught us how such explosions contribute to galaxy-wide chemical enrichment. Beyond its stellar populations, the Large Magellanic Cloud hosts fascinating large-scale structures. Its irregular shape, defined by a central bar and sprawling spiral arms, is not as clean or symmetric as typical spiral galaxies. This irregularity reflects its tumultuous history. Tidal forces from the Milky Way and interactions with the small Magellanic Cloud have distorted its disk and possibly triggered bursts of star formation. The bar itself, offset from the galaxy's center of mass, is believed to be a dynamically separate component, perhaps created or enhanced by gravitational disturbances. Its presence complicates models of the galaxy's mass distribution and internal dynamics. Another major structure is the LMC's warping disk. Unlike a perfectly flat plane, the LMC's stellar and gaseous disk is twisted and flared. This warp may result from tidal forces exerted by the Milky Way or from past mergers with smaller systems. As the galaxy orbits the Milky Way, these forces constantly tug at it, distorting its shape and possibly inducing density waves that compress gas and trigger star formation. Understanding the warp of the LMC can also shed light on similar phenomena seen in the Milky Way and other galaxies, helping us isolate the role of environment in shaping galactic morphology. Then there's the fascinating issue of the LMC's dark matter halo. Like all galaxies, the LMC is believed to be embedded in a halo of invisible matter that provides the gravitational glue holding it together. The extent and mass of this halo have become increasingly relevant to models of the Milky Way's future, as the LMC's incoming trajectory and speed suggest it may be more massive than once thought. Some models estimate the LMC's mass, including dark matter, to be as high as 200 billion solar masses. This figure significantly alters calculations of how it influences the Milky Way's halo, satellite system, and even its stellar disk. The dark matter in the LMC is not just a matter of theoretical interest, it affects observable phenomena as well. For instance, the gravitational lensing of background stars can provide clues about the distribution of dark matter within the LMC. Microlensing surveys have detected temporary brightening of stars as dark objects, possibly compact halo objects or machos, pass in front of them. While such events are rare, they are more easily observed in dense star fields like those found in the LMC, making it an ideal environment for studying this phenomenon. These observations serve as indirect evidence of the dark matter landscape enveloping the galaxy. Even more broadly, the LMC plays a critical role in the hierarchical structure of the local group. The local group, a collection of more than 50 galaxies dominated by the Milky Way and Andromeda, includes many smaller galaxies that orbit the two giants. The LMC is the largest satellite galaxy of the Milky Way and, due to its mass and motion, may not even be a true satellite in the traditional sense. Instead, some models propose that it is a recent interloper, a small galaxy group in its own right that was only captured by the Milky Way's gravity in the past few billion years. This changes how we interpret the accretion history of our galaxy and complicates the timeline of satellite interactions. These dynamics aren't limited to the LMC alone. Its gravitational partner, the Small Magellanic Cloud, SMC, is tightly bound to it in a dance that stretches back for billions of years. The two galaxies are connected by the Magellanic Bridge, a stream of stars and gas likely formed by mutual gravitational interaction. This bridge, visible in both HI observations and star counts, is an active region of star formation in its own right. The interaction between the LMC and SMC is believed to be the primary mechanism for stripping and redistributing this gas, and possibly even for triggering internal starburst activity in both galaxies. Further extending this interaction is the Magellanic Stream, a massive tail of gas that trails behind the LMC and SMC as they orbit the Milky Way. The stream stretches over 200 degrees across the sky and contains more than 1 billion solar masses of gas. Its origin remains a topic of debate. Some models suggest it was stripped by tidal forces, while others argue for ram pressure stripping as the clouds plowed through the Milky Way's hot halo gas. Either way, it represents a major channel for matter exchange between galaxies, and it may eventually rain down onto the Milky Way's disk, fueling future waves of star formation. As we follow the trail of the Magellanic Stream across the sky, it becomes clear that this immense structure isn't just an artifact of past gravitational violence. It's a living, evolving component of the Milky Way's broader ecosystem. The stream is composed primarily of neutral hydrogen gas, but also contains ionized and possibly molecular components. The distribution and ionization state of this gas are of keen interest to astronomers because they reveal how gas behaves in the galactic halo. Observations with radio telescopes, ultraviolet spectroscopy, and even space-based instruments have uncovered a complex internal structure, including filaments, knots, and cloudlets that hint at turbulent processes at work. This turbulence could be due to magnetic fields, hydrodynamic interactions, or even the influence of dark matter substructures. In particular, the presence of ionized gas in the Magellanic Stream suggests that it's being heated by interactions with the hot, diffuse halo gas of the Milky Way. This leads to a phenomenon known as ram pressure stripping, when a moving galaxy or gas cloud loses material due to pressure from the intergalactic medium. As the LMC and SMC plunge through the Milky Way's halo, they experience this pressure, which can strip gas from their outer regions and feed the stream. Understanding the physics of this process provides clues not only about the LMC's own structure, but also about how galaxies lose mass and evolve in group environments. And the story doesn't stop with the Magellanic Stream. A counterpart structure, known as the leading arm, extends ahead of the LMC and SMC in their orbital path. This arm is less massive and more diffuse than the stream trailing behind them, but its existence supports the idea that these two galaxies have undergone multiple orbits, or at least extended interactions, with the Milky Way. Some regions of the leading arm contain young stars, which implies that star formation can be triggered in even these tenuous intergalactic environments, possibly when clumps of gas fall into denser regions and collapse under their own gravity. Altogether, the LMC and its associated structures paint a picture of dynamic complexity. Far from being isolated, this galaxy is engaged in a web of interactions that stretch across space and time. These connections have reshaped not just the LMC itself, but the broader Milky Way environment. Streams of gas from the LMC may serve as a future reservoir for star formation in the Milky Way, particularly in its outskirts. The gravitational tugs from the LMC may perturb the orbits of stars in the Milky Way's disk and halo, contributing to structures like the galactic warp and disk flaring. In other words, this satellite galaxy may be actively shaping the larger galaxy it orbits. From a cosmological perspective, the LMC is a compelling analog for dwarf galaxies in the early universe. Its relatively low metallicity and ongoing star formation make it resemble the kinds of galaxies that were common during the epoch of reionization, the era when the first galaxies and quasars ionized the intergalactic medium. By studying the LMC up close, astronomers can calibrate models of how galaxies form and evolve under different conditions. For instance, Understanding how stars form in low metallicity environments helps us estimate star formation rates in distant galaxies whose light is just now reaching Earth from billions of years ago. The LMC's proximity also makes it a critical testing ground for astrophysical theories that are difficult to test in the more massive and chaotic Milky Way. One such area is stellar feedback, the process by which stars, especially massive ones, influence their surroundings through radiation, stellar winds, and supernova explosions. In the LMC, we can observe bubbles and cavities in the interstellar medium that are carved out by clusters of young stars. These bubbles are not just passive remnants. They actively compress surrounding gas, triggering new waves of star formation and driving the chemical evolution of the galaxy. By mapping these feedback effects, astronomers can refine simulations of galaxy evolution on all scales. On the topic of chemical evolution, the LMC presents a somewhat curious case. While it's less chemically enriched than the Milky Way, it's not nearly as primitive as the most metal-poor dwarf galaxies. Instead, it occupies a middle ground, offering a rich diversity of stellar populations that span a range of metallicities. By analyzing these stars spectroscopically, astronomers can trace the enrichment history of the galaxy, how successive generations of stars built up heavier elements through nuclear fusion and supernovae. This chemical timeline helps us piece together the formation history of the LMC and compare it to that of other galaxies, including our own. Moreover, chemical anomalies in certain stars, such as overabundances of carbon, nitrogen, or S-process elements, can signal past events like mass transfer in binary systems or pollution by asymptotic giant branch (AGB) stars. The distribution of such anomalies in the LMC's stellar populations provides clues to its internal mixing processes, initial mass function, and even merger history. Some stars show evidence of having formed in different environments, suggesting that the LMC may have cannibalized smaller galaxies in the past. These subtle fingerprints, preserved in the elemental composition of stars, allow astronomers to reconstruct galactic archaeology on a cosmic scale. The LMC also serves as a proving ground for cutting-edge instruments and observational techniques. Because it's so well positioned in the southern sky and rich in diverse phenomena, it's a frequent target for observatories like the Hubble Space Telescope, the Very Large Telescope, VLT, and the upcoming Vera C. Rubin Observatory. With new generations of spectrographs, adaptive optics, and space-based telescopes, scientists are now able to map the motions of stars, gas clouds, and even interstellar dust with unprecedented accuracy. These observations feed into increasingly sophisticated computer models that attempt to simulate the LMC's past and predict its future. One especially promising frontier involves the use of Gaia data to map the proper motions of stars in the LMC with exquisite precision. This allows astronomers to create three-dimensional velocity maps of the galaxy, revealing its internal rotation, disk thickness, and vertical structure. Such data have confirmed that the LMC rotates in a disk-like manner, albeit one that's warped and irregular. The motion of the stars also helps constrain the galaxy's gravitational potential, which in turn reveals the distribution of both visible and dark matter. These dynamics are critical to understanding how the LMC will continue to interact with the Milky Way, and what kind of structures will result from their eventual merger. Yes, the future holds a dramatic end for the LMC as a separate galaxy. Despite its current status as a companion to the Milky Way, the LMC is actually on a trajectory that will likely result in a full merger with our galaxy in the next few billion years. This event won't resemble a catastrophic collision, but rather a slow blending, as tidal forces strip stars and gas from the LMC and absorb them into the Milky Way's halo and disk. When this happens, the LMC may contribute to the thickening of the galactic disk, the reorganization of halo streams, and perhaps even the ignition of new star formation episodes fueled by the influx of its gas. Simulations of this process predict that the merger will leave observable signatures, new spiral arm structures, enhanced star formation rates, and kinematic anomalies in stellar motions. The LMC's dark matter halo, if it is indeed as massive as some models suggest, will also deliver a gravitational shock to the Milky Way's own halo. This could temporarily disrupt satellite systems and produce ripples in the stellar disk, some of which may already be visible today as wave-like perturbations detected by Gaia. Thus, the LMC is not just a satellite being studied, it is a cosmic sculptor that may reshape our galactic home from within. These anticipated transformations underscore the growing recognition that satellite galaxies like the LMC are not mere accessories to larger systems. They are agents of change. Their gravitational influence, their reservoir of gas and stars, and their eventual assimilation all serve as driving forces in the evolutionary timeline of galaxies like the Milky Way. In a sense, the LMC is a living fossil, a record-keeper of cosmic history and a foreteller of cosmic futures. What we learn from it echoes not just within our own galaxy, but across the universe, wherever similar galactic mergers are unfolding. This idea becomes even more compelling when we consider that the LMC is not the only satellite involved in this celestial ballet. Alongside it is the Small Magellanic Cloud, or SMC, a smaller, yet still influential galaxy that has been gravitationally linked to the LMC for billions of years. Their mutual gravitational attraction is evident not only from their proximity and synchronized motion but also from the presence of the Magellanic Bridge, a filament of gas and stars that connects them. This bridge, discovered through radio and optical observations, tells a story of interaction, of stars and gas being pulled and pushed across the vast emptiness of space as these two galaxies dance around one another. The dynamics between the LMC and SMC are a microcosm of galactic interaction in general. Simulations suggest that the SMC may have made several close passages around the LMC, each time disturbing its structure and contributing to the ejection of material into the Magellanic Stream. These encounters likely triggered bursts of star formation in both galaxies, as gravitational forces compressed gas and initiated collapse. In this way, the LMC is both a product of its own internal processes and the interactions with its smaller neighbor, just as it in turn affects the Milky Way on an even grander scale. Intriguingly, the LMC's interaction with the SMC may also explain some of the peculiarities in its structure. The LMC's bar is off-centered relative to its disk, a feature that has long puzzled astronomers. This asymmetry could be a relic of past gravitational tugs from the SMC or an echo of more ancient mergers. Similarly, the spiral arms of the LMC appear irregular and somewhat distorted, again suggesting a history marked by gravitational perturbation. By studying these structural anomalies in detail, astronomers can reconstruct the orbital histories of the Magellanic Clouds, providing a timeline of interactions and an estimate of how long they've been in the Milky Way's neighborhood. One of the most fascinating aspects of this long-term interaction is the role played by tidal stripping. As the LMC and SMC orbit one another, and together orbit the Milky Way, gravitational tides strip stars and gas from their outer regions, leaving behind faint streams and shells that trace their past paths. Some of these features are only now coming into view thanks to deep imaging surveys and the precise stellar motion data provided by missions like Gaia. These streams act like the trails of a cosmic comet, telling us where the galaxy has been and hinting at where it's going. The detection of such stellar debris is especially important because it allows astronomers to test models of dark matter distribution in and around the LMC. Dark matter, indeed, plays a pivotal role in the story of the Large Magellanic Cloud. While invisible to telescopes, its presence can be inferred from the motions of stars and gas, which move faster than they should if only normal matter were present. The LMC's rotation curve, how its stars orbit at different distances from the center, suggests the presence of a substantial dark matter halo. In fact, estimates of the LMC's total mass, including dark matter, range from 10 billion to over 100 billion solar masses. This has huge implications. A more massive LMC means stronger gravitational effects on the Milky Way, and it could even influence the orbits of other satellite galaxies. These implications are being explored through large-scale cosmological simulations that aim to recreate the local universe. By inputting different mass models for the LMC, scientists can predict how it would affect the motions of stars in the Milky Way's halo, the behavior of other satellites like the Sagittarius dwarf, and even the structure of the dark matter halo surrounding our galaxy. Some simulations suggest that the LMC may be carving a gravitational wake in the Milky Way's dark matter halo, a dense region of particles trailing in its path. This wake could in turn affect nearby satellites, perhaps pulling them into resonant orbits or altering their paths entirely. But the LMC's value isn't limited to its dynamical impact or its structural peculiarities. It also serves as a crucial calibration point in the cosmic distance ladder. As mentioned earlier, its relative proximity and the diversity of standard candles within it, such as Cepheid variables and RR Lyrae stars, make it an essential step in determining distances to farther galaxies. Any error in the LMC's distance propagates upward through the ladder, affecting the calibration of supernovae and the determination of the Hubble constant, the rate of cosmic expansion. Thus, fine-tuning our understanding of the LMC's distance and structure is a key component of precision cosmology. This precision is being pursued with increasing vigor. Observations with the Hubble Space Telescope and other instruments have narrowed the LMC's distance to within a few percent, but even small uncertainties matter. To that end, astronomers are using methods like detached eclipsing binaries, systems where two stars orbit each other in such a way that one periodically blocks the other, to determine absolute distances based on geometry and physics rather than empirical calibrations. These techniques are being refined and expanded, ensuring that the LMC continues to serve as a cornerstone of our understanding of the cosmos. Beyond its scientific utility, the LMC holds a place in the cultural history of astronomy. Its visibility in the southern skies has made it an object of curiosity for centuries, long before telescopes or astrophysics. In modern times, the LMC has become an enduring target for amateur astronomers, astrophotographers, and professional researchers alike. Its wealth of nebulae, star clusters, and supernova remnants make it a treasure trove for visual and scientific exploration. The Tarantula Nebula alone, with its complex filaments and active star-forming regions, is one of the most popular astrophotography subjects in the southern hemisphere. Even a modest telescope reveals its sprawling beauty, while large observatories dissect its innermost workings in detail. Few other galaxies offer such accessibility and richness in one compact package. This accessibility has also made the LMC a prime target for citizen science. Projects that invite the public to classify stars, trace gas clouds, or identify variable stars often include data from the LMC, bringing more eyes and minds into the scientific process. These efforts not only accelerate discovery, but also foster a deeper appreciation for the universe among the general public. As data volumes grow in the era of big surveys, the role of the public in helping parse the LMC's secrets may become even more essential. Ultimately, the Large Magellanic Cloud is more than just a nearby galaxy. It is a laboratory, a time machine, a messenger, and a cosmic partner. It embodies the grand themes of astrophysics: formation, interaction, evolution, and destiny. It is a participant in a drama that spans billions of years and extends across millions of light years, a drama that continues to unfold before our eyes and instruments. Every photon we capture from the LMC is a message from a distant past, every gravitational tug of force shaping the future. To study it is to engage with the cosmos on both a personal and universal level. The Large Magellanic Cloud also plays an invaluable role in testing and refining theoretical astrophysics. Because it is close enough for individual stars to be resolved, yet large and diverse enough to host a wide range of stellar populations and environments, it offers a unique testbed for comparing theoretical models of stellar evolution, galaxy formation, and chemical enrichment against observable reality. Every model built to explain the broader universe must first survive the scrutiny of the LMC's data, making it a kind of proving ground for cosmological theory. One of the ways in which the LMC advances our understanding of the life cycles of stars is through its extensive population of asymptotic giant branch, AGB stars. These are evolved, luminous red stars in a late stage of stellar evolution, characterized by thermal pulses and heavy mass loss. AGB stars play a critical role in enriching the interstellar medium with elements such as carbon, nitrogen, and S-process elements, which are forged in their interiors and ejected through stellar winds. Because the LMC's lower metallicity differs from that of the Milky Way, its AGB population provides insight into how these stars evolve under different chemical conditions. Additionally, the LMC's planetary nebulae, the glowing remnants of intermediate mass stars, are ideal laboratories for studying the final phases of stellar life. Their structures, emission lines, and chemical compositions offer a wealth of information about the stellar mass loss process and the formation of white dwarfs. These planetary nebulae vary in morphology, including spherical, bipolar, and irregular forms, and by studying them in the LMC, astronomers can better isolate the effects of environment, age, and progenitor mass on their development. The LMC also contains hundreds of globular clusters and open clusters, many of which are among the most massive and well-preserved in the local universe. These clusters allow for direct studies of stellar dynamics, binary evolution, and the initial mass function. Because all stars in a cluster are formed roughly at the same time and from the same material, they provide a controlled environment for testing models of how stars change over time. Moreover, some of the LMC's clusters span a wide age range, from very young to ancient, offering a timeline of star formation over billions of years. One notable feature of the LMC's star cluster system is its apparent age gap. While the Milky Way contains clusters that span a continuous range of ages, the LMC exhibits a noticeable gap between about 3 and 10 billion years ago, where relatively few clusters are found. This so-called age gap has been the subject of significant study, and various theories have been proposed to explain it, ranging from galactic interactions with the SMC to internal feedback processes that temporarily halted star formation. Understanding this feature helps refine theories of cluster formation and survival, and provides clues to the LMC's dynamic history. The chemical enrichment history of the LMC is another area of active research. Unlike the Milky Way, which shows a steady buildup of metals over time, the LMC's chemical evolution is more episodic, with bursts of enrichment tied to periods of enhanced star formation. By studying the abundances of various elements in stars of different ages, astronomers can reconstruct the galaxy's history of supernova events, gas inflow and outflow, and internal mixing. In particular, spectroscopic surveys of red giant stars in the LMC have revealed detailed patterns of elemental abundance that are helping to refine models of nucleosynthesis and galactic chemical evolution. These patterns also shed light on the relative contributions of different types of supernovae. Type 2 supernovae, which result from the collapse of massive stars, dominate early in a galaxy's life and enrich the interstellar medium with alpha elements like oxygen, magnesium, and silicon. Type Ia supernovae, which result from white dwarf explosions in binary systems, occur later and add iron peak elements. The ratio of alpha to iron in stars tells astronomers when different types of supernovae became dominant, and how rapidly star formation was proceeding at different epochs in the LMC's past. The LMC's interstellar medium, the gas and dust between stars, is also a focal point of study. It contains complex networks of molecular clouds, HI regions, and diffuse atomic gas, all of which participate in the cycle of star formation. Observations in radio, infrared, and submillimeter wavelengths have mapped the distribution of these components with increasing precision. These studies are revealing how gas condenses into stars, how young stars influence their surroundings, and how feedback from supernovae shapes the broader environment. The LMC's lower metallicity compared to the Milky Way also makes it a valuable analog for understanding conditions in early galaxies. Among its many roles, the LMC has become essential for understanding the formation of massive stars and the impact they have on their surroundings. Massive stars are short-lived but exert profound influence through their intense radiation, powerful winds, and explosive deaths as supernovae. The Tarantula Nebula is a prime example, a stellar nursery where massive stars are born, live violently, and die young, all within the span of a few million years. Studying these processes in real time helps refine simulations of starburst galaxies and the feedback mechanisms that regulate galaxy growth. In addition, the LMC offers a near-perfect setting for studying supernova remnants, SNRs. These are the expanding shells of gas and dust left behind after a supernova explosion, and they are crucial for understanding the physics of shock waves, cosmic ray acceleration, and the interaction between stellar ejecta and the interstellar medium. Because of the LMC's known distance and relatively low extinction, its SNRs can be studied in exquisite detail across multiple wavelengths. The diversity of remnants, ranging from young, compact shells to older, more diffuse structures, provides a timeline of how these explosions evolve and influence their surroundings. One particularly important SNR in the LMC is the remnant of SN 1987A. This was the closest observed supernova since Kepler's supernova in 1604, and the first visible to the naked eye in modern times. Its detection in 1987 was a landmark moment in astronomy, allowing scientists to directly study the collapse of a massive star in a neighboring galaxy. SN 1987A has been monitored continuously since its explosion, revealing insights into neutrino emission, shock wave propagation, and the formation of neutron stars. It has fundamentally advanced our understanding of stellar death, and it continues to serve as a dynamic laboratory more than 35 years later. Even today, astronomers keep a close eye on the LMC in the hopes of catching more transient events, novae, gamma-ray bursts, X-ray binaries going into outbursts, and possibly even future supernovae. The rich stellar populations, combined with high-quality time-domain surveys, make the LMC an ideal region for capturing the universe in motion. Each of these events, fleeting as they may be, contributes another piece to the vast puzzle of astrophysical phenomena. As technology continues to improve, so too will our understanding of the LMC. Next-generation telescopes like the James Webb Space Telescope, JWST, the Vera C. Rubin Observatory, and the Extremely Large Telescope, ELT, are poised to deliver unprecedented resolution and sensitivity. These instruments will peel back even more layers of the LMC's structure, uncovering fainter stars, more distant clusters, and previously unseen gas structures. With this new data, the LMC's role as a galactic laboratory will only grow stronger, offering new insights that were once beyond our reach. The JWST, for instance, is particularly well-suited for studying the dust-enshrouded regions of the LMC where new stars are forming. Its infrared capabilities allow it to penetrate dust clouds that would obscure even the most powerful optical telescopes. By analyzing the spectral fingerprints of molecules and dust grains, astronomers can investigate the conditions that lead to star formation and track the chemical evolution of protostellar environments. These observations will complement existing datasets from Spitzer and Herschel, filling in gaps in our understanding and providing a fuller picture of stellar genesis in the LMC. Meanwhile, the Rubin Observatory will open a new chapter in time-domain astronomy. By scanning the entire southern sky every few nights, it will detect countless transient events in the LMC, from variable stars to explosive phenomena. Its massive data stream will allow for real-time alerts and coordinated follow-up, enabling scientists to observe rare events from start to finish. In this way, the LMC will continue to serve not just as a static snapshot of the cosmos, but as a dynamic, evolving entity. The Extremely Large Telescope, ELT, currently under construction in Chile, promises to revolutionize our understanding of galaxies like the Large Magellanic Cloud. With its 39-meter primary mirror and adaptive optics system, the ELT will provide unprecedented resolution, enough to discern individual stars and stellar systems within the LMC at a level of detail never before achieved. This capability will allow astronomers to study the atmospheres of individual stars, measure their chemical compositions with extraordinary precision, and even detect planets orbiting stars in the LMC. Imagine the implications of discovering exoplanets in another galaxy. Such a breakthrough would fundamentally expand the scope of exoplanetary science. Moreover, the ELT will enable direct observations of the initial mass function, IMF, in environments very different from those in the Milky Way. The IMF describes the distribution of stellar masses at birth and is a foundational concept in astrophysics, shaping everything from the luminosity of galaxies to the evolution of star clusters. Whether or not the IMF is universal has long been debated, and the LMC, with its distinct environment, offers a powerful testing ground. If the IMF varies significantly in the LMC, it would have profound consequences for our models of galaxy evolution across the cosmos. Alongside large telescopes, radio arrays like the Square Kilometre Array, SKA, will offer new views of the LMC in radio wavelengths. The SKA's sensitivity will allow astronomers to map neutral hydrogen with fine resolution, revealing the LMC's internal gas dynamics in exquisite detail. This will enable new studies of turbulence, inflow and outflow of gas, and the impact of stellar feedback on the interstellar medium. Furthermore, the SKA will help identify pulsars within the LMC, rotating neutron stars emitting beams of radio waves. These pulsars can be used as cosmic clocks, providing insight into the physics of ultra-dense matter and even acting as tools for testing the predictions of general relativity. In the realm of high-energy astrophysics, X-ray and gamma-ray observatories continue to probe the hottest and most violent processes within the LMC. Space-based telescopes such as Chandra, XMM Newton, and NuSTAR have detected numerous X-ray binaries, systems where a compact object like a neutron star or black hole accretes matter from a companion star. These binaries are essential for understanding how massive stars end their lives, how black holes form, and how angular momentum and magnetic fields influence accretion. The LMC hosts a disproportionate number of high-mass X-ray binaries relative to the Milky Way, suggesting that its lower metallicity somehow favors their formation. Gamma-ray observations have also uncovered emissions from the decay of radioactive isotopes like aluminum-26 and iron-60, ejected by massive stars and supernovae. These isotopes serve as markers for recent nucleosynthesis and provide insight into the ongoing chemical enrichment of the galaxy. Studying their distribution helps trace the locations of recent supernovae and the movement of enriched material through the galaxy's interstellar medium. In the near future, new missions such as Athena, Advanced Telescope for High-Energy Astrophysics, and the proposed Lynx X-ray Observatory are expected to take these investigations even further. These missions will provide sharper imaging, better sensitivity, and faster timing resolution, allowing us to study the physics of compact objects and energetic outbursts in the LMC with new levels of clarity. We may eventually be able to directly observe matter spiraling into black holes in the LMC, or track the evolution of magnetars, highly magnetized neutron stars, within its young stellar populations. Yet beyond the realm of pure astrophysics, the Large Magellanic Cloud also influences our understanding of galactic ecosystems and the broader architecture of the cosmos. It represents an intermediate case between large spiral galaxies like the Milky Way and small dwarf spheroidal galaxies, helping to bridge the gap in our models of galaxy morphology and formation. It blurs the line between satellite and primary galaxy, especially when its interactions with the small Magellanic Cloud and the Milky Way are considered. Its presence prompts questions about hierarchical galaxy formation, the idea that large galaxies grow by accreting smaller ones. The LMC itself may have been a central galaxy of its own small group before falling into the Milky Way's gravitational influence. Some researchers have even proposed that the LMC brought along a cohort of smaller satellite galaxies that now accompany it, akin to how the Milky Way has the LMC and SMC as companions. If true, this would suggest a kind of satellites of satellites structure in the local group, mirroring predictions from simulations of dark matter halos in cosmology. Moreover, the dark matter halo of the LMC is thought to be massive, possibly in the range of 10 to the power of 11 solar masses, nearly one-tenth that of the Milky Way. This substantial halo helps stabilize the LMC against tidal disruption and contributes to the Milky Way's own dark matter distribution. As the LMC orbits and eventually merges with the Milky Way, it will deposit both baryonic and dark matter into our galaxy's halo, altering its mass profile and dynamics. This event will affect not only the structure of the Milky Way, but also the orbits of its stars, star formation rates, and the overall morphology of the galaxy. Recent simulations suggest that the LMC's influence on the Milky Way is already measurable. The outer halo of our galaxy shows signs of a wake, a distortion in the dark matter distribution believed to be caused by the gravitational tug of the LMC's passage. This wake could help astronomers detect and map dark matter, which remains invisible except through its gravitational effects. In this sense, the LMC becomes a kind of probe or test particle, revealing the unseen structure of our galaxy's invisible skeleton. The coming merger of the LMC with the Milky Way, predicted to occur within the next 2 to 3 billion years, will be a major event in the Milky Way's history. Unlike the slow and subtle accretion of dwarf spheroidal galaxies, the LMC's infall will be dramatic, capable of inducing spiral arms, triggering star formation, and potentially feeding gas into the central supermassive black hole of the Milky Way. It may leave a lasting imprint in the form of tidal streams, new clusters, and shifts in galactic dynamics. In a sense, the LMC is not just a visitor, it is a future building block of our own galaxy. All of these threads, stellar evolution, galactic dynamics, dark matter interactions, chemical enrichment, cosmological implications, are interwoven into the story of the Large Magellanic Cloud. It is not merely a point of light in the southern sky or a peripheral neighbor of the Milky Way. It is a vast, complex, and living system that continues to shape our understanding of the universe. Its stars are our laboratories, its clouds are textbooks, and its movements are clues to the hidden structure of the cosmos. In every wavelength and at every scale, the LMC tells a story. It is a story written in the language of light, dust, motion, and time, a story that is still unfolding with every new observation, every new theory, and every new discovery. For the astronomer, the LMC is both a familiar companion and a deep mystery. And for humanity, it is a reminder that even the night sky, so seemingly still, is filled with worlds in motion and secrets waiting to be uncovered. The Large Magellanic Cloud, in its rich complexity, continues to beckon humanity's most advanced minds and instruments, offering a dynamic canvas upon which nearly every major branch of astrophysical science can project its questions. As we peer deeper into its structure and behavior, we realize that the LMC is not just a passive object awaiting observation, it is an active participant in the cosmic drama of galactic evolution, turbulence, stellar life cycles, and even the shaping of our own galactic neighborhood. One fascinating area of research revolves around the peculiar stellar populations that the LMC harbors. Among these, a striking feature is the abundance of blue supergiants, massive, luminous stars that shine intensely and burn through their fuel rapidly. Their presence and distribution across the LMC hint at recent bursts of star formation, especially within its bar and spiral-like structures. These blue supergiants serve not only as beacons of stellar youth but also as indicators of the interplay between gas density, turbulence, and feedback-driven starburst episodes. Adding further richness to the LMC's stellar tapestry is the existence of rare types of variable stars, such as Cepheids and our Lyrae stars. These pulsating variables are invaluable as standard candles, objects whose intrinsic brightness is known and can be used to measure cosmic distances. Because the LMC contains a wide range of such variables, it has played a crucial role in calibrating the extragalactic distance scale. This makes it instrumental in refining measurements of the Hubble constant, which quantifies the expansion rate of the universe. In fact, much of our current understanding of the distance ladder, how we determine distances to faraway galaxies, rests on the solid foundation provided by careful measurements of variable stars in the LMC. Moreover, the LMC's relatively low metallicity presents a pristine environment for studying early universe star formation processes. Metallicity refers to the abundance of elements heavier than hydrogen and helium, and lower metallicity is typically associated with earlier cosmic times. Thus, by observing how stars form and evolve in the metal-poor conditions of the LMC, astronomers can simulate the conditions of the early universe. For instance, lower metallicity affects how massive stars lose mass over time, which in turn influences whether they end their lives as neutron stars, black holes, or parent stability supernovae, a rare and powerful explosion that might explain some of the most energetic phenomena observed in the distant universe. Another intriguing topic concerns the abundance and structure of globular clusters within the LMC. These ancient spherical assemblies of stars are key to unraveling the galaxy's early history. One particularly famous LMC globular cluster is NGC 1866, which defies conventional wisdom by containing stars of differing ages, suggesting that globular clusters may not be as simple as once believed. The study of such objects in the LMC has prompted a rethinking of how globular clusters form, evolve, and interact with their host galaxies. In addition to globular clusters, the LMC is also home to a variety of young open clusters, offering a snapshot of stellar formation in its most recent phase. These clusters often lie embedded within the galaxy's dust lanes and emission nebulae, where the ultraviolet radiation from young stars excites the surrounding hydrogen gas, causing it to glow in the red hues characteristic of H-alpha emission. Detailed spectroscopic studies of these regions can reveal the chemical fingerprints of the gas, helping scientists track the enrichment of heavy elements over time. And it's not just individual stars or clusters that make the LMC compelling, it's also the enigmatic large-scale structures that stretch across the galaxy. The LMC's disk, though often described as irregular, contains hints of spiral arms and even a central bar, a densely packed region that may influence the motion of stars and gas throughout the galaxy. Interestingly, the bar itself appears to be offset from the center of the galaxy's overall stellar distribution, suggesting that interactions with the Milky Way or Small Magellanic Cloud may have distorted the LMC's original structure. This bar, surrounded by a more extended, warped disk, reflects a history of gravitational interactions. These distortions are not mere curiosities. They're signatures of past encounters, dynamic collisions, and tidal forces acting over millions of years. As simulations grow more advanced, astronomers can better model these interactions to trace the LMC's orbital path and reconstruct the precise moments when it passed close to the Milky Way or its sibling, the Small Magellanic Cloud. These encounters likely sparked waves of star formation, altered the galaxy's trajectory, and even pulled out gas to form massive structures like the Magellanic Stream. Speaking of the Magellanic Stream, this vast ribbon of gas extending from the LMC and SMC across a large fraction of the southern sky is one of the most spectacular features associated with these galaxies. Composed mainly of neutral hydrogen, the stream spans over 100 degrees of arcade on the sky and contains a significant mass of gas, potentially enough to fuel star formation in the Milky Way for hundreds of millions of years. The exact origin of the stream is still debated, whether it resulted from tidal stripping by the Milky Way, mutual interactions between the clouds, or a combination of both, but its importance is unquestioned. The Magellanic Stream is more than a trail of debris, it is a galactic ecosystem in flux. It contains both neutral and ionized gas, as well as small star-forming clumps. It interacts with the Milky Way's hot halo, possibly producing shocks and turbulence that may be visible in X-rays or ultraviolet wavelengths. The study of how this gas accretes onto the Milky Way offers insights into how galaxies grow through the infall of fresh material from their surroundings. Further, the stream may contain clumps of dark matter, or at the very least, follow the gravitational contours sculpted by it. As such, tracking the motion of gas clouds within the stream could help map the Milky Way's dark matter halo, a monumental challenge in astronomy. In this sense, the LMC isn't just a subject of study, but an indirect tool helping us probe the invisible scaffolding of our galaxy. In more speculative realms, some scientists have considered whether the LMC might host intelligent life. While no evidence exists for extraterrestrial civilizations there, the sheer number of stars, tens of billions, makes it a tantalizing thought. With the coming generations of telescopes, it may even become possible to search for biosignatures or technosignatures from planets within the LMC, although such detections would push current technology to its limits. Still, in a universe full of wonders, the idea is not beyond consideration. Even in the field of gravitational wave astronomy, the LMC may play a role. The mergers of compact objects like neutron stars or black holes, events that generate gravitational waves detectable by observatories like LIGO and Virgo, could occur within the LMC. Indeed, the detection of such an event within the LMC would offer a unique opportunity to study gravitational waves in a different galactic environment and test our understanding of gravity and spacetime. The potential for future discovery is limitless. As our instruments become more sensitive, our data sets more complete, and our models more sophisticated, the Large Magellanic Cloud will remain a cornerstone of astrophysical research. Its unique properties and proximity make it not only a fascinating object in its own right, but also a cosmic laboratory that informs our knowledge of galaxies, stars, planets, and the universe itself. The LMC is more than a distant cloud of stars, it is a bridge. A bridge between the nearby and the far away. A bridge between the simple and the complex. A bridge between what we know and what we have yet to learn. And as long as humanity keeps looking up, seeking to understand the vastness of the cosmos, the Large Magellanic Cloud will continue to shine, not only as a light in the southern sky but as a beacon guiding us deeper into the mysteries of the universe. The Large Magellanic Cloud, with all its diverse phenomena, continues to serve as one of the most important testbeds for understanding galactic evolution. One of the most intriguing aspects of the LMC is its potential role in the study of galactic interactions. The LMC is part of a dynamic trio of galaxies, alongside the Small Magellanic Cloud, SMC, and our very own Milky Way. These galaxies are in a constant gravitational tug-of-war, and the effects of these interactions ripple through the structure of the galaxies involved. While we may think of galaxies as relatively stable, their histories are often filled with dramatic events, and the LMC is no exception. It is believed that the LMC was once a much smaller galaxy, but over time, interactions with the Milky Way and the SMC have altered its shape and structure, contributing to its current form. These interactions may have sparked star formation, triggered gas outflows, and contributed to the creation of the Magellanic Stream. The gravitational effects between the LMC, the SMC, and the Milky Way continue to play a significant role in shaping the future trajectory of the LMC and could also provide valuable insight into the larger processes that govern the evolution of galaxies throughout the universe. One particularly interesting aspect of the LMC is the sheer variety of star formation it hosts. The galaxy is home to stars of all ages and sizes, from ancient stars to young, hot blue supergiants, and everything in between. These stars are scattered across the LMC's disk and bar, and the star formation rate of the galaxy has varied significantly over time. The most recent star formation has been concentrated in the central bar and along the spiral arms, where dense clouds of gas and dust are still actively collapsing into new stars. The stellar population of the LMC is an important piece of the puzzle for understanding the broader processes of galactic evolution. By studying the distribution of stars, their ages, and their compositions, astronomers can gain a deeper understanding of how the LMC has evolved over time, how star formation processes work in low metallicity environments, and how such galaxies compare to other members of the local group, such as the Milky Way and the Andromeda Galaxy. The LMC's role in the larger cosmic structure is also an important point of study. As a satellite galaxy of the Milky Way, the LMC offers a unique opportunity to examine the interactions between a small galaxy and its much larger neighbor. The tidal forces from the Milky Way have likely played a significant role in the LMC's evolution, influencing its morphology and star formation activity. The LMC is gradually being pulled toward the Milky Way, and over the course of millions of years, it may be absorbed into our galaxy, potentially adding its stars and gas to the Milky Way's larger population. One particularly fascinating area of research focuses on the chemical composition of the LMC. The galaxy's relatively low metallicity, compared to the Milky Way, provides a window into the conditions of star formation in the early universe. Metallicity refers to the proportion of elements heavier than hydrogen and helium in a star, and a low metallicity indicates that the stars formed from gas that had been less enriched by the elements produced in earlier generations of stars. Studying the LMC's stellar populations allows astronomers to examine how stars form and evolve in environments that resemble the conditions of the early universe, before heavy elements like carbon, oxygen, and iron were abundantly produced by previous generations of stars. One of the most striking features of the LMC is its vast network of nebulae, particularly the iconic 30 Doradus, also known as the Tarantula Nebula. This enormous star-forming region is one of the most active and well-studied areas of star formation in the local group of galaxies. It is home to some of the most massive stars ever discovered, and its intense radiation and stellar winds have sculpted the surrounding gas and dust into stunningly beautiful shapes. The Tarantula Nebula serves as a natural laboratory for studying the processes of star formation, the evolution of massive stars, and the feedback mechanisms that regulate these processes. In addition to the Tarantula Nebula, the LMC is home to a wealth of other stellar nurseries, many of which are actively forming stars. These regions are filled with gas and dust, which are slowly collapsing under the force of gravity to create new stars. The feedback from these stars, in the form of ultraviolet radiation, stellar winds, and supernova explosions, is constantly reshaping the surrounding environment, driving the cycle of star formation and destruction. The LMC is also a key player in the study of supernovae. Supernovae, the explosive deaths of massive stars, are responsible for dispersing heavy elements into the interstellar medium, enriching future generations of stars and planets. The LMC has been the site of several supernovae in recent decades, with one of the most famous being supernova 1987A. This event was one of the closest supernovae to Earth in modern times and provided an unprecedented opportunity to study the mechanics of a supernova explosion. The remnants of supernova 1987A continue to be a subject of intense study, offering valuable insights into the behavior of collapsing stars and the formation of neutron stars and black holes. Supernovae also play a critical role in the creation of cosmic rays, high-energy particles that travel through space at nearly the speed of light. These particles are produced in the aftermath of supernovae, and their study can provide clues about the processes that govern the most extreme events in the universe. Observing the supernova remnants in the LMC and other galaxies helps astronomers understand the physical conditions in these violent environments and how cosmic rays are accelerated and propagate through space. The gravitational interactions between the LMC and the Milky Way have been ongoing for billions of years, and the future of the LMC is likely to be shaped by these forces. It is thought that the LMC is gradually being pulled toward the Milky Way, and in a few billion years, it may eventually merge with our galaxy. This merger would have profound effects on the structure of both galaxies, potentially triggering bursts of star formation and reshaping their overall dynamics. The study of these interactions provides valuable insights into the processes of galactic mergers, a common feature in the evolution of galaxies throughout the universe. One of the key aspects of studying the LMC is understanding its position within the larger cosmic web. The LMC is part of the Local Group of Galaxies, a collection of more than 50 galaxies, including the Milky Way, Andromeda, and several smaller satellite galaxies. The Local Group itself is part of the larger Laniakea supercluster, which contains thousands of galaxies stretching across vast distances. By studying the LMC and its interactions with other galaxies in the Local Group, astronomers can better understand the dynamics of galaxy clusters, the flow of gas between galaxies, and the role of dark matter in shaping the large-scale structure of the universe. The LMC's proximity to the Milky Way and its interactions with the SMC also make it a valuable target for studying the distribution of dark matter. Dark matter, an invisible substance that makes up a significant portion of the mass in the universe, has been detected through its gravitational effects on galaxies and galaxy clusters. By observing how the LMC moves under the influence of gravity, astronomers can gain insights into the distribution of dark matter in both the LMC and the Milky Way. This can help refine our understanding of the properties of dark matter and its role in the formation and evolution of galaxies. In recent years, the LMC has also become a focal point for the study of cosmic inflation, the rapid expansion of the universe in its earliest moments. Observations of the LMC and its surrounding structures provide crucial information about the distribution of matter and energy in the early universe, helping to test and refine models of inflation. By studying the LMC, astronomers can gain a better understanding of how the universe evolved from a hot, dense state to the vast, complex cosmos we observe today. The future of the LMC, and its eventual fate, remains a subject of great interest for astronomers. As the LMC continues to interact with the Milky Way and the SMC, it will likely experience further tidal forces, star formation bursts, and gas accretion. Whether it will eventually be absorbed into the Milky Way, form new structures, or evolve into something entirely new is a question that will continue to drive research for years to come. The Large Magellanic Cloud is not just another distant galaxy, it is a dynamic, evolving system that offers unparalleled opportunities for studying the complexities of galactic evolution. From its star formation processes and chemical composition to its role in the larger cosmic web, the LMC is a natural laboratory that continues to provide valuable insights into the workings of the universe. As we continue to explore its mysteries, we deepen our understanding of the fundamental processes that shape galaxies and the universe itself. As we delve deeper into the understanding of the Large Magellanic Cloud, LMC, it becomes evident that its significance extends beyond its proximity to the Milky Way or its place within the local group. The LMC stands as a unique testament to the diverse processes that govern galactic behavior, offering astronomers a window into galactic interactions, star formation, and the elusive nature of dark matter. While our view of the LMC from Earth is spectacular, it also prompts a multitude of questions about how the universe operates on larger scales, and how the forces shaping one galaxy may have implications for the broader cosmos. One of the enduring aspects of the LMC's importance in astronomical research is its status as a low metallicity galaxy. The term metallicity refers to the abundance of elements heavier than hydrogen and helium in a galaxy's stars, nebulae, and gas clouds. The LMC, with its lower metallicity compared to the Milky Way, offers a glimpse into the conditions of galaxies in the early stages of the universe. Galaxies like the LMC, which are metal poor, are considered closer in nature to the first galaxies that formed after the Big Bang. Studying the star-forming regions of the LMC allows us to learn about the processes by which stars, planets, and other celestial bodies formed in the early universe, a critical step in understanding the evolution of the cosmos. The metal content of a galaxy is directly tied to the processes that occurred in previous generations of stars. In galaxies with higher metallicity, there are more heavy elements, which are crucial for forming planets, creating a diversity of life forms, and even influencing the course of star formation. In contrast, galaxies with lower metallicity, like the LMC, have stars that form from a gas supply that contains fewer heavy elements. This means that the stars in the LMC are often more similar to the stars that existed in the early universe, offering a snapshot of star formation conditions in the primordial cosmos. The study of the LMC's metal-poor environment provides insights into the life cycle of stars. The LMC hosts numerous young, massive stars that were born in regions such as the Tarantula Nebula. These stars, while short-lived, generate immense amounts of energy and enrich their surroundings with their powerful radiation and stellar winds. As they age and eventually explode as supernovae, they seed the surrounding gas with heavier elements, gradually enriching the environment. The low metallicity of the LMC allows researchers to observe this process more clearly, providing clues about how the universe gradually evolved from a state dominated by hydrogen and helium to the chemically rich state we observe today. While the star-forming regions of the LMC are a captivating feature, the older, redder stars of the galaxy offer an entirely different perspective. These stars, which reside primarily in the outer regions of the LMC, are relics of an earlier era in the galaxy's history. These older stars are essential for understanding the past evolutionary processes of the galaxy, including how the LMC may have formed and how its structure has evolved over time. By studying the ages and compositions of these stars, astronomers can gain valuable insights into the history of the LMC, including when it began to form its first stars, and how it has been shaped by its interactions with the Milky Way and the small Magellanic Cloud. In terms of stellar remnants, the LMC also provides a unique laboratory for studying neutron stars, black holes, and supernova remnants. Supernovae are an inevitable outcome for massive stars, and the LMC's ongoing star formation ensures that these catastrophic events continue to occur, providing astronomers with an ongoing source of study. The supernova remnants in the LMC are particularly valuable for understanding the final stages of a star's life cycle and how these events influence the interstellar medium. The remnants of past supernovae, including the remnants of supernova 1987A, remain a key target for ongoing research, as they offer an opportunity to investigate the nature of these cataclysmic explosions and their role in shaping the structure of galaxies. Supernova 1987A itself is a critical event in the history of astrophysical research. This was the closest supernova to Earth in over 400 years, and it provided an unprecedented opportunity to observe the processes of a massive star's death. In the years following the explosion, astronomers observed the formation of a nebula of gas and dust around the site of the supernova, while also detecting the emission of neutrinos, tiny subatomic particles, just moments after the explosion. These observations helped to confirm long-standing theories about the collapse of a star's core into a neutron star, providing vital clues about the mechanisms behind supernovae. The legacy of Supernova 1987A continues to shape our understanding of stellar evolution and the formation of neutron stars, black holes, and other exotic objects. Another facet of the LMC's intriguing behavior lies in its interaction with the Small Magellanic Cloud, SMC, a neighboring galaxy that, like the LMC, is also a satellite of the Milky Way. The gravitational tug-of-war between the LMC and SMC has resulted in tidal interactions that have dramatically shaped both galaxies. These interactions have led to the formation of the Magellanic Stream, a vast trail of gas that connects the two galaxies and stretches for hundreds of thousands of light-years. The stream is a remnant of an ancient collision between the LMC and SMC, and it contains clues about the past behavior of these galaxies. The presence of the Magellanic Stream is an important piece in the puzzle of galaxy evolution. By studying the gas that forms the stream, astronomers can investigate the processes that occur during galactic interactions, including how gas is stripped from one galaxy and transferred to another. The interaction between the LMC and SMC, as well as the associated tidal forces, have also influenced the distribution of dark matter in the region, adding an additional layer of complexity to the study of these galaxies. The Magellanic Stream is a visual manifestation of the gravitational forces at play between these two galaxies and serves as a reminder of the dynamic nature of the universe. Dark matter, which makes up a significant portion of the mass in galaxies, is another aspect of the LMC that continues to intrigue researchers. While dark matter is invisible and cannot be detected directly, its presence can be inferred from its gravitational effects on visible matter. In the case of the LMC, astronomers have used the motion of stars and gas clouds to estimate the amount of dark matter in the galaxy. The presence of dark matter in the LMC offers insights into the distribution of this mysterious substance in small galaxies and provides a point of comparison for the study of dark matter in larger galaxies like the Milky Way. Dark matter also plays a key role in the study of galaxy formation and evolution. The distribution of dark matter within a galaxy can influence its overall shape and dynamics, and studying how the LMC's dark matter interacts with the visible matter in the galaxy can help us understand the fundamental processes that govern the formation of galaxies. The gravitational pull of dark matter is thought to be responsible for holding galaxies together and preventing them from flying apart, even though dark matter itself cannot be observed directly. By studying the distribution of dark matter in the LMC, astronomers can refine their models of galaxy formation and evolution. As the LMC continues to evolve, the dynamics of its interactions with both the Milky Way and the Small Magellanic Cloud will continue to shape its future. Over time, the LMC may be gradually drawn into the Milky Way, adding its stars, gas, and dark matter to our galaxy's structure. Such a merger would likely trigger bursts of star formation and alter the structure of both galaxies. Studying the LMC's current interactions with its neighbors provides a unique opportunity to investigate the processes that occur during galaxy mergers, which are a common feature in the history of galaxies across the universe. Ultimately, the Large Magellanic Cloud stands as one of the most fascinating objects in our cosmic neighborhood. It is a living laboratory that provides an unparalleled view into the processes of star formation, supernovae, and galactic evolution. Its interactions with the Milky Way and the Small Magellanic Cloud serve as a reminder of the dynamic and ever-changing nature of the universe. By continuing to study the LMC, astronomers will undoubtedly uncover new insights into the workings of galaxies, the role of dark matter, and the fundamental processes that govern the evolution of the cosmos. As we move forward in exploring the Large Magellanic Cloud, LMC, it's important to dive deeper into the intricate dynamics of its star formation processes. The LMC is an active site of star birth, and the way stars come into existence here holds a wealth of information that enriches our understanding of stellar evolution. Unlike more evolved galaxies like the Milky Way, which have a relatively balanced population of old and new stars, the LMC is more heavily skewed toward the younger, high-mass star population. These stars, often formed in massive stellar nurseries, are the brightest and most energetic objects in the galaxy, and their characteristics provide essential insights into the forces driving star formation. The largest and most well-known star-forming region in the LMC is the Tarantula Nebula, also known as 30 Doradus, an area where the conditions for star formation are optimal. The Tarantula Nebula is often regarded as one of the most massive and active star-forming regions in the local group of galaxies. Within its vast clouds of gas and dust, new stars are born in a spectacular process that involves the collapse of molecular clouds, which condense under their own gravity to form dense cores. These cores heat up, and nuclear fusion begins, resulting in the birth of a new star. The Tarantula Nebula contains several massive young stars, which emit intense ultraviolet radiation that causes the surrounding gas and dust to ionize, creating the nebula's glowing appearance. However, star formation in the LMC is not a uniform process. While regions like the Tarantula Nebula are teeming with new stars, there are also older, more evolved regions within the galaxy where star formation has slowed or ceased altogether. These areas are home to older stars, many of which were formed in the early history of the galaxy. By comparing the properties of stars from different regions within the LMC, astronomers can study the evolution of the galaxy and the varying conditions under which stars form. The star formation rate in the LMC is also closely tied to its environment and interactions with neighboring galaxies. The tidal forces between the LMC and the Milky Way, as well as the gravitational pull from the Small Magellanic Cloud, have significant effects on the gas and dust within the LMC. These interactions can trigger bursts of star formation, especially when gas is compressed by gravitational forces, which can lead to the rapid formation of new stars. This is one of the reasons why the LMC is often referred to as a starburst galaxy. The process of star formation in the LMC is dynamic and constantly evolving, making it a rich source of study for astronomers interested in the mechanisms that drive the birth and death of stars. The stars in the LMC are also a key component of the galaxy's chemical evolution. Stars, particularly massive ones, are responsible for producing heavy elements such as carbon, oxygen, and iron through the process of nuclear fusion. These elements are then released into the surrounding interstellar medium when stars die, enriching the gas clouds that will eventually form the next generation of stars. The low metallicity of the LMC means that the galaxy is in the early stages of this process, and studying its stars allows astronomers to track the progress of this chemical evolution over time. Understanding how stars in the LMC have contributed to the enrichment of the galaxy can shed light on the broader processes that shape the evolution of galaxies throughout the universe. In addition to its star-forming regions, the LMC also contains a wealth of other cosmic phenomena that make it an intriguing subject for study. Among the most fascinating are the various remnants of supernovae and other explosive events. Supernovae are the violent deaths of massive stars, and they play a crucial role in shaping the structure of galaxies. The remnants of these explosions are often seen as nebulae, which consist of the ejected material from the star's core. These remnants are essential for understanding the life cycles of stars and the role they play in dispersing heavy elements into the surrounding environment. The LMC is home to several well-known supernova remnants, with one of the most famous being the remnant of supernova 1987A. This supernova, which exploded in 1987, was the closest supernova to Earth observed in more than 400 years. The explosion provided astronomers with an unparalleled opportunity to study the death of a massive star and the subsequent formation of a supernova remnant. Since its discovery, astronomers have been closely monitoring the expanding remnant, which is providing valuable data about the nature of supernovae, the mechanics of stellar explosions, and the formation of neutron stars. The remnant of supernova 1987A has also helped astronomers understand the phenomenon of neutrino emission, which occurs during a supernova explosion. Neutrinos are subatomic particles that interact only very weakly with matter, making them difficult to detect. However, when a supernova explodes, a burst of neutrinos is emitted, carrying away vast amounts of energy. In 1987, the detection of neutrinos from the supernova provided direct evidence for the process of core collapse supernovae, helping to confirm long-held theories about the death of massive stars. In addition to supernova remnants, the LMC is also home to a variety of other stellar remnants, including neutron stars and black holes. These objects are the remnants of massive stars that have undergone gravitational collapse at the end of their lives. Neutron stars, which are incredibly dense objects composed almost entirely of neutrons, are thought to be the collapsed cores of stars that were not massive enough to become black holes. These objects emit intense radiation, and some are observed as pulsars, which produce periodic bursts of electromagnetic radiation as they spin rapidly. The LMC is an excellent laboratory for studying neutron stars and pulsars, as the galaxy's active star formation rates ensure a steady supply of these objects. Black holes, on the other hand, are the result of the collapse of the most massive stars. These objects have such strong gravitational fields that not even light can escape from them, making them invisible to traditional telescopes. However, their presence can be inferred by observing the effects they have on nearby objects. In the case of the LMC, there are several suspected black holes that are thought to exist in binary star systems, where a black hole pulls material from a companion star. This material forms a hot, glowing accretion disk, which emits X-rays that can be detected by space-based observatories. The study of stellar remnants in the LMC is essential for understanding the final stages of stellar evolution and the processes that govern the formation of black holes and neutron stars. These objects are some of the most extreme and enigmatic phenomena in the universe, and studying them can provide valuable insights into the nature of space, time, and gravity. The gravitational dynamics of the LMC are another crucial area of study. The galaxy's interactions with the Milky Way and the Small Magellanic Cloud have played a significant role in shaping its structure and evolution. The LMC is part of a gravitationally bound system known as the Magellanic Group, which also includes the Small Magellanic Cloud and other smaller satellite galaxies. These galaxies are in constant motion, and their mutual gravitational interactions have led to a variety of interesting phenomena, including tidal interactions and the formation of the Magellanic Stream. The Magellanic Stream is a vast cloud of gas that stretches across hundreds of thousands of light-years, connecting the LMC and the Small Magellanic Cloud. The stream is thought to be the result of a past collision between the two galaxies, during which gas was stripped from the galaxies and left in a long, trailing filament. This structure provides valuable information about the dynamics of galaxy interactions and the role of tidal forces in shaping the intergalactic medium. The gravitational interactions between the LMC and the Milky Way are also of great interest to astronomers. These interactions have led to the distortion of the LMC's shape, and they are thought to play a role in the galaxy's ongoing star formation activity. As the LMC moves through the gravitational field of the Milky Way, it experiences periodic compressions of gas that can trigger bursts of star formation. These interactions also influence the distribution of dark matter within the galaxy, making the study of the LMC a key component in understanding the role of dark matter in galaxy formation and evolution. The LMC's position as a satellite galaxy of the Milky Way means that it is not immune to the gravitational influences of our own galaxy. Over time, the LMC may be slowly pulled toward the Milky Way, where it could eventually merge with our galaxy. Such a merger would have profound consequences for both galaxies, potentially triggering waves of star formation and altering the structure of the Milky Way. However, this process is likely to take billions of years, and the eventual fate of the LMC remains uncertain. The Large Magellanic Cloud is a fascinating and complex galaxy that continues to captivate the imaginations of astronomers and researchers. Its proximity to the Milky Way, its active star formation, its stellar remnants, and its interactions with other galaxies make it an invaluable object of study. The LMC is a living laboratory that offers a glimpse into the processes that shape galaxies, stars, and the universe as a whole. As our understanding of this remarkable galaxy continues to grow, it will undoubtedly provide new insights into the nature of the cosmos and the forces that govern its evolution. As we continue to explore the Large Magellanic Cloud, LMC, it's essential to understand its role within the larger cosmic framework, especially in terms of its interaction with other galaxies. The LMC is not isolated in the universe. Instead, it is part of a larger group of galaxies known as the Magellanic System. This system includes the Small Magellanic Cloud, SMC, as well as other smaller dwarf galaxies and stellar remnants that orbit around the Milky Way. The relationship between these galaxies is crucial for understanding the overall structure of the local group of galaxies, to which both the LMC and the Milky Way belong. The gravitational relationship between the LMC and the SMC is particularly intriguing. These two galaxies are bound together in a complex orbital dance. Despite their close proximity to one another, they are very different in terms of their sizes, structures, and the history of their interactions. The LMC, being much larger and more massive than the SMC, exerts a significant gravitational influence over its smaller neighbor. In fact, the mutual gravitational attraction between the two galaxies is so strong that it has shaped their mutual orbits, causing them to pass through each other in the distant past, with effects that we can still observe today. One of the most fascinating aspects of this relationship is the Magellanic Stream, a vast, faint cloud of hydrogen gas that stretches across the sky. This stream is believed to be the result of tidal interactions between the LMC and the SMC, causing gas to be stripped from both galaxies and left in a long, trailing filament. The Magellanic Stream provides crucial insights into the nature of galaxy interactions and the ways in which galaxies influence the surrounding intergalactic medium. By studying this stream, astronomers can gain a deeper understanding of the processes that shape galaxy dynamics, gas flows, and the role of dark matter in these interactions. The ongoing interaction between the LMC and the Milky Way also plays a central role in shaping the galaxy's structure. Although the LMC is currently in the process of moving away from the Milky Way, the gravitational pull from our galaxy has had a significant impact on its evolution. Over billions of years, the LMC and the Milky Way have passed through each other, with the LMC being slowly pulled toward our galaxy. This interaction has distorted the shape of the LMC, and in the future, it could lead to a merger between the two galaxies. Such a merger would not be a sudden or catastrophic event. In fact, when galaxies collide, they tend to pass through one another without direct collisions between stars due to the vast distances between individual stars. However, the gravitational forces exerted during such a merger would trigger significant changes in both galaxies. In the case of the LMC and the Milky Way, this interaction could lead to the formation of new stars, as gas clouds are compressed by the gravitational forces. The merger could also alter the overall structure of the Milky Way, potentially leading to the creation of a new galactic shape, such as a barred spiral or an elliptical galaxy. The fate of the LMC is still uncertain, and it is likely to remain an object of study for astronomers for years to come. Whether the LMC will merge with the Milky Way or remain a satellite galaxy for billions of years, it is clear that the gravitational forces between these two galaxies will continue to shape the evolution of both. Understanding the complex dynamics of galaxy interactions is crucial for understanding the broader processes of galaxy formation, evolution, and the role of dark matter in shaping the universe. One of the most intriguing aspects of the LMC is its role in the study of dark matter. Dark matter is an elusive and invisible substance that is thought to make up a significant portion of the universe's total mass. While dark matter cannot be directly observed, its presence can be inferred by studying the gravitational effects it has on visible matter, such as stars and gas. The LMC, with its relatively low mass and low metallicity, provides an excellent opportunity to study dark matter in a different context than the Milky Way. Recent studies of the LMC's rotation curve, how its stars move through space, have revealed valuable information about the distribution of dark matter within the galaxy. In particular, the fact that the stars in the LMC continue to orbit at a constant speed, even at great distances from the galaxy's center, suggests that a significant amount of unseen mass is present, providing the necessary gravitational pull. The study of dark matter in the LMC is helping astronomers refine their models of how dark matter is distributed within galaxies and how it influences galaxy dynamics. Another aspect of dark matter that has been a subject of considerable research is the role it plays in the formation and evolution of galaxies. While the precise nature of dark matter remains unknown, it is believed to play a crucial role in the formation of galaxies by providing the necessary gravitational framework in which visible matter can accumulate. Without dark matter, galaxies like the LMC would likely not have the structure or mass they possess today. Dark matter may also influence the rate of star formation and the distribution of gas within galaxies, making it an essential component of the galaxy's overall behavior. The study of the Large Magellanic Cloud and its dark matter content is also relevant for understanding the broader mystery of dark matter in the universe. Because the LMC is relatively nearby and has been studied in great detail, it provides a unique opportunity to test theories about dark matter in a galactic environment. By observing the LMC, astronomers can test how dark matter interacts with visible matter and refine their understanding of its properties. This research could have significant implications for our understanding of the universe, as dark matter is believed to constitute around 27% of the total mass and energy in the universe. Its role in shaping galaxies, clusters of galaxies, and the large-scale structure of the universe is crucial for understanding the cosmic landscape. Beyond the realms of dark matter and galaxy interactions, the LMC has also contributed to our understanding of the chemical enrichment of galaxies. The process of chemical enrichment refers to the gradual accumulation of heavier elements in a galaxy as stars evolve and explode, releasing their elements back into the interstellar medium. These elements are then recycled into new generations of stars, planets, and other objects. The LMC, with its relatively low metallicity compared to the Milky Way, provides valuable insights into the early stages of chemical enrichment. The gas and dust in the LMC are composed of fewer heavy elements, which suggests that the galaxy has not yet gone through as many generations of star formation as the Milky Way. Studying the chemical composition of stars and gas in the LMC allows astronomers to track the progress of chemical enrichment in the galaxy and learn more about the processes that govern the formation of heavy elements. The study of stellar populations in the LMC has also revealed important information about the history of star formation in the galaxy. Unlike the Milky Way, which has a broad range of star ages, the LMC has a more uniform population of younger stars. This suggests that star formation in the LMC has been relatively recent, with bursts of activity occurring over the last few billion years. By comparing the ages and metallicities of stars in the LMC, astronomers can learn more about the galaxy's star formation history and the processes that have shaped its evolution. In terms of the cosmic timeline, the Large Magellanic Cloud occupies an intriguing place. It is a prime example of a galaxy in the process of being shaped by its environment. While it may not be as massive or as old as the Milky Way, it provides essential insights into the early stages of galaxy formation and evolution. The LMC's interactions with the Milky Way and the SMC, its star formation processes, and its dark matter content all contribute to the understanding of the broader mechanisms at work in galaxy formation. The LMC also serves as a valuable tool for studying the broader universe. Its proximity allows astronomers to study the effects of various cosmic phenomena in a relatively accessible context. By understanding how galaxies like the LMC evolve, interact, and change over time, scientists can gain deeper insights into the processes that govern the larger universe. Whether it's the formation of stars, the distribution of dark matter, or the dynamics of galaxy interactions, the Large Magellanic Cloud remains one of the most important galaxies in the local group, offering invaluable clues about the universe's past, present, and future. It is evident that this galaxy is much more than just a satellite of the Milky Way. It is a dynamic, evolving system that continues to provide crucial insights into the processes of galaxy formation, star formation, and cosmic evolution. The LMC may be a relatively small galaxy in terms of size, but its role in the larger cosmic context is anything but insignificant. Through its interactions with other galaxies, its rich population of stars, and its mysteries of dark matter and chemical enrichment, the LMC remains an essential focus of astronomical research. As our tools and techniques for observing distant galaxies continue to improve, there is no doubt that the Large Magellanic Cloud will continue to be a key object in the quest to understand the universe and its many wonders. As we continue to probe deeper into the intricacies of the Large Magellanic Cloud, LMC, it's important to delve into the more subtle and lesser-known aspects of this fascinating galaxy. Beyond its interactions with the Milky Way and its role in helping us understand dark matter, the LMC also plays a significant role in the study of stellar evolution, supernovae, and the complex interplay of stellar populations. The LMC provides astronomers with an extraordinary laboratory for studying the life cycle of stars. The galaxy's relatively low metallicity means that stars in the LMC are born with fewer heavy elements than those in the Milky Way. This difference allows astronomers to observe stellar evolution in a purer, more primordial state, offering a glimpse into the processes that shape the first generations of stars in the universe. Studying these stars gives us valuable insight into how stars evolve over time, especially in environments with less influence from the heavier elements that are more common in older galaxies like the Milky Way. A particular focus of this study has been the formation of massive stars in the LMC. Because the galaxy has experienced significant bursts of star formation, it offers an opportunity to observe the formation and evolution of stars that are far more massive than those in our own galaxy. Massive stars burn through their fuel much more quickly than smaller stars, leading to their spectacular death in supernovae. The rapid cycle of birth and death of massive stars provides a fascinating window into the life and death of stars in a relatively youthful environment. The LMC is home to several well-known star-forming regions, most notably the Tarantula Nebula, one of the most active star-forming regions in the local group. The Tarantula Nebula, also known as 30 Doradus, is a stellar nursery where new stars are constantly being born. In fact, this nebula is the most massive and luminous star-forming region known in our neighborhood of the universe. It is also home to some of the most massive and hottest stars ever discovered, many of which will eventually end their lives in supernovae. The Tarantula Nebula provides an exceptional opportunity for astronomers to study the formation of high-mass stars and the processes that drive star formation in a large, active nebula. One of the most significant discoveries in the Tarantula Nebula is the presence of extremely massive stars that challenge our understanding of stellar evolution. Some of these stars are over 100 times more massive than the Sun, a size that is difficult to replicate in the Milky Way due to its higher metallicity. The study of these stars can help astronomers refine their models of stellar formation and evolution, particularly in environments that are less enriched in heavy elements. Furthermore, the intense radiation and powerful stellar winds produced by these massive stars have a profound impact on their surroundings, often triggering further star formation, while also preventing the gas and dust from collapsing into new stars. The massive stars of the LMC play an important role in our understanding of supernovae. Supernovae are the explosive deaths of massive stars, and they are crucial to the chemical enrichment of the universe. When a star explodes in a supernova, it ejects vast amounts of gas and heavy elements into space, seeding the interstellar medium with the building blocks for future generations of stars, planets, and life. The study of supernovae in the LMC helps astronomers understand the different types of supernovae and how they affect the surrounding environment. It also sheds light on the process of stellar nucleosynthesis, the creation of heavier elements in the cores of stars, and how those elements are distributed throughout the universe after a supernova explosion. The LMC has also provided us with valuable information about the rate of supernovae in different galactic environments. The most famous supernova observed in the LMC was supernova 1987A, a Type II supernova that exploded in the Tarantula Nebula in 1987. This event was one of the most studied supernovae in history, as it occurred relatively close to Earth and allowed astronomers to observe the explosion in great detail. Supernova 1987A provided a wealth of information about the final stages of a massive star's life and the physical processes that take place during a supernova explosion. It also allowed astronomers to refine their models of supernovae and their role in the cosmic ecosystem. Supernovae are not the only stellar phenomenon that the LMC offers for study. The galaxy is also home to a variety of other interesting stellar objects, including star clusters, pulsars, and variable stars. The study of these objects can provide insight into the dynamics of stellar populations and the processes that govern the evolution of stars within a galaxy. For example, the LMC contains several large star clusters, which are groups of stars that form together from the same gas cloud. By studying these clusters, astronomers can learn about the initial conditions of star formation and how clusters evolve over time. Some of these star clusters, such as the 47 Tucani, are older and more evolved, providing an opportunity to study the later stages of stellar evolution. Pulsars, the rapidly spinning remnants of massive stars that have gone supernova, are another fascinating feature of the LMC. These objects emit regular bursts of radiation and are some of the most extreme and enigmatic objects in the universe. By studying pulsars in the LMC, astronomers can gain a deeper understanding of the physics of neutron stars, the dense remnants of supernova explosions. Pulsars also provide valuable information about the interstellar medium, as their radiation can be used to probe the gas and dust between stars. In addition to these fascinating stellar phenomena, the LMC is home to a variety of variable stars. These stars change in brightness over time, and their fluctuations can provide valuable information about their internal structure and the processes occurring within them. Variable stars in the LMC are particularly interesting because they allow astronomers to study the effects of low metallicity on stellar behavior. By analyzing the light curves of these stars, astronomers can learn about the processes that drive stellar variability and gain insight into the conditions that lead to the formation of variable stars. Another important aspect of the Large Magellanic Cloud stellar populations is the presence of its intermediate-age stars. These stars, which are older than the young stars in regions like the Tarantula Nebula but younger than the oldest stars in the galaxy, offer valuable insights into the history of star formation in the LMC. By studying the age and metallicity of these stars, astronomers can piece together a timeline of star formation in the LMC and learn about the factors that have influenced the galaxy's evolution over time. Understanding the distribution of intermediate-age stars also helps astronomers learn about the role of external factors, such as interactions with the Milky Way, in shaping the galaxy's stellar populations. The LMC's unique position in the local group of galaxies also makes it an important object for studying the larger-scale structure of the universe. The galaxy provides a valuable opportunity to examine the properties of dwarf galaxies and how they interact with their larger neighbors. Because the LMC is a member of the local group, which also includes the Milky Way, the Andromeda Galaxy, and a number of smaller galaxies, it provides important clues about the formation and evolution of galaxy clusters. The interaction between the LMC and the Milky Way has shaped the structure of both galaxies, and studying these interactions can help astronomers understand the broader processes that govern the formation of large-scale cosmic structures. At the same time, the LMC's relatively low mass and simple structure make it an excellent subject for studying the basic building blocks of galaxies. The galaxy provides a pristine environment for studying the fundamental processes of galaxy formation, such as the accretion of gas and the formation of stars and stellar clusters. Understanding how these processes unfold in the LMC can provide critical insights into the early stages of galaxy formation and the conditions that lead to the creation of more complex galaxies like the Milky Way. Furthermore, the LMC has contributed to the study of cosmology and the expansion of the universe. Its distance from Earth, combined with its well-studied stellar populations, has made it a key object for measuring cosmic distances. By analyzing the LMC's Cepheid variable stars, especially pulsating stars whose periods of oscillation are directly related to their intrinsic brightness, astronomers have been able to refine measurements of cosmic distances and improve our understanding of the rate of expansion of the universe. These measurements, in turn, have played a crucial role in determining the value of the Hubble constant, a fundamental parameter in cosmology. The Large Magellanic Cloud is much more than a mere satellite of the Milky Way. It is a vibrant, complex galaxy that has significantly advanced our understanding of the universe. From its role in the study of dark matter and galaxy interactions to its contributions to stellar evolution, supernovae, and cosmology, the LMC is a cornerstone of modern astrophysical research. Its proximity to Earth, combined with its rich stellar populations and active star-forming regions, makes it a unique and invaluable laboratory for studying a wide range of cosmic phenomena. As our ability to observe and analyze distant galaxies continues to improve, there is no doubt that the Large Magellanic Cloud will remain a focal point of astronomical discovery, helping us unlock the many mysteries of the cosmos. The Large Magellanic Cloud, LMC, continues to intrigue astronomers for numerous reasons. As we shift our focus to the broader implications of its study, it's important to understand how the LMC's role extends beyond our immediate cosmic neighborhood, helping to answer profound questions about the universe's origins, evolution, and the fundamental forces that govern it. By examining not only the LMC's intrinsic properties but also its relationship with other galaxies, we are able to trace the journey of galaxies across cosmic time, offering us unparalleled insights into the history and future of the universe. One of the most compelling features of the LMC is its unique position within the local group. As a satellite of the Milky Way, the LMC plays an important role in understanding how galaxies interact. The relationship between the two galaxies is particularly interesting because the LMC is not only a gravitationally bound member of the Milky Way's satellite system but also an essential object for understanding the mechanics of galaxy mergers and interactions. As the LMC orbits the Milky Way, its gravitational interactions have left their mark on both galaxies, offering valuable data on how these interactions might influence star formation, galaxy morphology, and the long-term evolution of galaxies. Galactic interactions, particularly between the LMC and the Milky Way, offer insight into the larger processes that shape the evolution of the cosmos. For instance, the LMC's interactions with the Milky Way's massive spiral structure could be responsible for various phenomena, such as star formation bursts and changes in the distribution of dark matter. The Milky Way's gravity influences the movement and trajectory of the LMC, and in return, the LMC's gas clouds have been pulled into the Milky Way's outer reaches, leading to a complex exchange of materials. This interaction could explain the presence of certain unusual stellar populations found in both galaxies, including some stars that seem to have been stripped from one galaxy and deposited into the other. These ongoing interactions provide a natural experiment for studying the processes that govern galaxy evolution over time. The relationship between the LMC and the Milky Way can also help refine our understanding of dark matter. The LMC's low mass means it is much more sensitive to the effects of dark matter than larger galaxies like the Milky Way. Some researchers have proposed that the LMC could hold the key to understanding how dark matter behaves in smaller galaxies. The LMC's gravitational interactions with the Milky Way may also provide a natural test bed for hypotheses regarding dark matter and its role in galaxy formation. For example, the way in which the LMC moves in relation to the Milky Way could offer insights into the distribution and properties of dark matter in both galaxies. Another intriguing aspect of the LMC's interaction with the Milky Way is its potential to reveal information about the history of star formation in the local group. By studying the effects of past galactic interactions, astronomers can piece together a timeline of how the LMC, the Milky Way, and other galaxies in the local group have evolved over the billions of years. This information provides essential clues about how galaxies in general form and evolve, and the role that environmental factors, such as gravitational interactions, gas accretion, and the availability of dark matter, play in shaping a galaxy's future. The presence of ancient, low metallicity stars in the LMC, for example, hints at a history of star formation that is very different from that of the Milky Way, which is characterized by a much more evolved stellar population. The LMC's interaction with the Milky Way and its effects on star formation also tie into the broader study of cosmic chemistry. The LMC's lower metallicity, as compared to the Milky Way, provides an invaluable opportunity to examine the early stages of chemical enrichment in the universe. As stars in the LMC go through their life cycles, they produce heavy elements through nuclear fusion, which are then dispersed into the interstellar medium after supernovae. This process of chemical enrichment is essential for understanding the formation of planets, stars, and even life. By studying the chemical composition of stars in the LMC, astronomers can compare the elemental makeup of early stars with those in more evolved galaxies like the Milky Way, helping to map out the process of stellar evolution across different cosmic environments. The study of supernovae in the LMC also contributes to this understanding of chemical enrichment. Supernovae not only distribute heavy elements into the surrounding interstellar medium but also trigger the formation of new stars by compressing nearby gas and dust. These elements, including carbon, oxygen, and iron, are essential for the formation of planets, life, and the chemical processes that shape galaxies. By studying how supernovae in the LMC distribute heavy elements, astronomers can better understand the role that these explosive events play in the creation of galaxies and the formation of life-supporting conditions in the universe. Moreover, The LMC's proximity to the Milky Way provides an excellent opportunity to compare the rates of supernovae in different galactic environments, allowing researchers to understand how the rate of supernovae affects the overall evolution of a galaxy. On a cosmological scale, the LMC provides valuable insights into the expansion of the universe. As one of the closest galaxies to the Milky Way, its stellar populations are relatively easy to observe, and its well-understood distance and size make it an ideal object for studying the rate of cosmic expansion. The LMC's Cepheid variable stars are of particular interest in this context. These stars have a well-established relationship between their pulsation period and luminosity, allowing astronomers to use them as standard candles to measure distances in the universe. By using the LMC's Cepheid variables to measure distances, astronomers can refine their measurements of the Hubble constant, the rate at which the universe is expanding. This has profound implications for our understanding of the universe's age, the nature of dark energy, and the ultimate fate of the cosmos. The LMC is also a valuable object for studying the formation of stellar populations in environments with lower metallicity. While the Milky Way's higher metallicity means it has more of the heavy elements necessary for planet formation and life, the LMC's lower metallicity provides a unique opportunity to study the formation of stars and planets under different conditions. For example, the LMC's relatively low levels of heavy elements make it an ideal laboratory for studying the formation of the first generation of stars in the universe. These stars, known as population 3 stars, are thought to have formed from the primordial gas left over from the Big Bang, and their study can shed light on the processes that led to the creation of the first galaxies and stars. Interestingly, the LMC's interactions with the Milky Way may have also influenced the formation of stellar populations. Gravitational interactions between the two galaxies may have caused bursts of star formation in the LMC, leading to the creation of new generations of stars. Studying the distribution and age of stars in the LMC can reveal how these interactions have affected the galaxy's evolution and helped shape its stellar populations. Furthermore, the LMC's stellar populations provide insight into how stars in low metallicity environments evolve differently from those in more metal-rich galaxies. This has important implications for understanding the overall process of star formation in the universe, as well as the conditions that are necessary for the formation of planets and life. As we continue to explore the wonders of the LMC, it becomes clear that this galaxy offers an exceptional opportunity to study the fundamental processes that shape the universe. From its active star formation regions to its unique stellar populations and its relationship with the Milky Way, the LMC is a rich source of knowledge that will continue to inform and inspire generations of astronomers. By observing the LMC, we gain insights not only into the nature of galaxies but also into the broader forces that govern the evolution of the cosmos itself. The Large Magellanic Cloud, with its unique characteristics, its star-forming regions, and its interactions with the Milky Way, serves as both a window into the past and a laboratory for understanding the future of our own galaxy. The insights gained from studying the LMC are essential not only for our understanding of stellar evolution, but also for our broader quest to unravel the mysteries of the universe. From its early star formation to its role in shaping the Milky Way and its impact on our understanding of dark matter, the LMC remains a cornerstone of modern astrophysical research. As we delve deeper into the mysteries of the Large Magellanic Cloud, we are constantly uncovering new layers of knowledge that help refine our understanding of galactic evolution, star formation, and the dynamics of intergalactic interactions. One aspect of the LMC that has long fascinated astronomers is its high level of activity in terms of star formation. The galaxy's star-forming regions, including the Tarantula Nebula, are not only some of the most energetic places in the LMC but also some of the most studied regions in the entire universe. These nebulae represent an extreme example of star formation, where massive, young stars are born in vast clusters, and their intense radiation drives the surrounding gas to higher temperatures. The Tarantula Nebula, in particular, stands out as one of the most active stellar nurseries known to humanity. With a diameter of about 1,000 light-years, it is one of the largest star-forming regions in the local group of galaxies, and the cluster of stars it houses is among the most massive ever discovered. These star clusters play an essential role in understanding how star formation proceeds in an environment with low metallicity, as is the case in the LMC. The presence of such massive stars in the Tarantula Nebula, many of which have short lifespans but powerful stellar winds and supernova explosions, dramatically influences the surrounding gas, which, in turn, affects the star formation processes. The interaction between these young stars and the surrounding nebula leads to a cycle of creation and destruction that may very well serve as a model for understanding how galaxies evolve over time. What makes the Tarantula Nebula even more remarkable is the insight it provides into the early stages of star formation in low metallicity environments. Stars born in such environments are often referred to as population II stars, which are believed to be among the first stars to have formed in the universe. Studying these stars and their surrounding nebulae can shed light on how the first generations of stars impacted the chemical composition of the universe, laying the foundation for the formation of galaxies and planetary systems in the aftermath of the Big Bang. Furthermore, understanding how these massive, metal-poor stars interact with their environment can help us predict the types of supernovae that may occur and the consequences of such explosive events on the interstellar medium. The role of massive stars in the evolution of the LMC extends beyond their effects on star formation. As these stars reach the end of their life cycles, they undergo dramatic supernova explosions that inject heavy elements into the surrounding gas. These elements are crucial for the formation of new stars, planets, and potentially life. The LMC's population of massive stars is thought to play a critical role in enriching the interstellar medium with the heavy elements necessary for future generations of stars and planets to form. This process of chemical enrichment is essential for understanding how galaxies evolve over time, and the LMC provides a unique opportunity to study this phenomenon in a galaxy that is relatively close by. In addition to its active star-forming regions, the LMC also hosts a variety of other interesting structures, such as the Large Magellanic Stream. This is a long, extended stream of gas that stretches over 200,000 light-years and is thought to be the result of the LMC's past interactions with the Milky Way. The stream is composed of gas that has been stripped from the LMC by the Milky Way's gravity, and it provides important clues about the gravitational interactions between the two galaxies. By studying the Large Magellanic Stream, astronomers can gain insights into how these interactions have affected the structure and evolution of both the LMC and the Milky Way. The Large Magellanic Stream is not the only feature that connects the LMC to its larger neighbor. The LMC's orbit around the Milky Way, along with the tidal forces exerted by the Milky Way's gravity, has had a significant impact on the LMC's structure and evolution. These tidal forces have stretched the LMC, creating a distorted shape that is characteristic of many galaxies that have experienced close interactions with larger galaxies. The resulting asymmetry of the LMC provides astronomers with an opportunity to study how tidal forces influence the morphology of galaxies. The shape and behavior of the LMC, as influenced by the Milky Way's gravity, offer important lessons about the complex processes of galaxy evolution. The gravitational pull of the Milky Way also plays a significant role in shaping the distribution of stars and gas within the LMC. One of the key observations that has emerged from studies of the LMC is the presence of a tilted disk. The disk of the LMC is not aligned with its outer regions, and this misalignment is believed to be the result of interactions with the Milky Way. Over the course of billions of years, the Milky Way's gravity has influenced the motion of stars and gas within the LMC, leading to the tilted configuration we observe today. This misalignment offers valuable insights into how gravitational interactions shape the internal dynamics of galaxies and can be used to test models of galaxy formation and evolution. In addition to its interaction with the Milky Way, the LMC is also thought to be involved in a larger cosmic context, influencing the formation and behavior of neighboring galaxies. One of the most interesting aspects of the LMC's role in the broader universe is its potential influence on other galaxies in the local group. The LMC's gravitational interactions with the Milky Way could have a cascading effect on other galaxies in the region, affecting their shape, size, and star formation activity. The study of these interactions can help astronomers understand how galaxy groups evolve over time, and how the mutual gravitational pull between galaxies can influence the formation of galaxy clusters. As we examine the LMC in its broader context, we are reminded of the vast scale of the universe and the interconnectedness of all cosmic phenomena. The LMC, though a relatively small galaxy in the grand scheme of the universe, plays a crucial role in shaping our understanding of the cosmos. Its proximity to the Milky Way, combined with its rich stellar populations, active star-forming regions, and complex interactions with its larger neighbor, makes it a unique and invaluable laboratory for studying the fundamental processes of galaxy evolution. The study of the LMC, its interactions with the Milky Way, and its role in the broader universe is far from over. As new technologies and more advanced telescopes come online, our ability to study distant galaxies like the LMC will only improve. The future of astronomical research promises exciting new discoveries, as we continue to unravel the mysteries of the LMC and its place in the cosmos. Each new observation, each new data point, brings us closer to understanding the dynamic and ever-changing nature of the universe. As we look to the future, the Large Magellanic Cloud will undoubtedly continue to play a pivotal role in shaping our understanding of the universe. From its star-forming regions to its interactions with the Milky Way, the LMC is a key piece of the puzzle in understanding the complex processes that drive galactic evolution. Its proximity to the Milky Way, along with its rich and varied structure, makes it an invaluable object for astronomical research. Whether we are studying its supernovae, its chemical composition, or its role in the evolution of nearby galaxies, the LMC offers unparalleled insights into the workings of the universe, and its story is far from finished. Through the study of the LMC, we not only gain a deeper understanding of this particular galaxy but also expand our knowledge of the cosmos as a whole. As we continue to explore the mysteries of the Large Magellanic Cloud, we are reminded of the vastness and complexity of the universe, and the ever-present desire to uncover its secrets. The LMC is a living, dynamic system, constantly evolving and providing new insights into the processes that shape galaxies, stars, and the universe itself. The more we learn about the LMC, the more we understand about the nature of our own galaxy, the Milky Way, and our place in the cosmos. The Large Magellanic Cloud stands as a testament to the beauty and complexity of the universe, a reminder that even in our own cosmic backyard, there is still so much left to discover. Whether we are observing its stellar populations, studying its interactions with the Milky Way, or investigating the origins of the elements that make up our universe, the LMC offers us a glimpse into the past, present, and future of the cosmos. It is a galaxy that continues to inspire awe, wonder, and scientific curiosity, and it will undoubtedly remain a central focus of astronomical research for years to come. The Large Magellanic Cloud's remarkable characteristics make it a constant subject of interest not only because of its proximity to our own galaxy, the Milky Way, but also due to its potential to offer insights into some of the most profound questions about galaxy formation, stellar evolution, and the overall dynamics of the universe. As a relatively small and irregular galaxy, the LMC provides a unique contrast to the more typical spiral galaxies that dominate the universe, such as the Milky Way. This distinction allows astronomers to examine the processes that drive galactic growth and evolution in a way that would be difficult to observe in larger, more massive galaxies. One particularly intriguing aspect of the LMC is the nature of its irregular shape. Unlike the well-defined disk structure of spiral galaxies like the Milky Way, the LMC is classified as an irregular galaxy, which means it lacks the symmetry and clearly defined arms that are characteristic of spiral galaxies. The irregular shape of the LMC is thought to be a direct result of its interactions with the Milky Way, particularly through tidal forces exerted by the larger galaxy. These tidal forces have caused significant distortions in the structure of the LMC, stretching and pulling it into its current configuration. In addition to tidal interactions with the Milky Way, the LMC's relatively small mass and lack of a significant central bulge further contribute to its irregular appearance. The absence of a central bulge, a common feature in spiral galaxies, suggests that the LMC has a unique history of star formation and evolution. Rather than undergoing the process of gradual buildup through mergers and accretions that form the dense cores seen in other galaxies, the LMC's formation is likely the result of a more chaotic and complex series of interactions. This chaotic history has left a lasting imprint on the galaxy's structure, producing a more diffuse, less ordered system of stars and gas. Furthermore, the irregular shape of the LMC presents an opportunity for astronomers to investigate the role of external forces, such as gravitational interactions with other galaxies, in shaping the morphology and dynamics of galaxies. By studying the LMC's distortions, scientists can gain insights into how such interactions occur and how they affect the overall structure of galaxies over time. This research can, in turn, help to refine our understanding of the processes that drive galaxy formation and evolution across the universe. Another fascinating feature of the Large Magellanic Cloud is its relatively low metallicity compared to other galaxies. The chemical composition of a galaxy, particularly the abundance of elements heavier than hydrogen and helium, plays a crucial role in the formation and evolution of stars. The LMC's low metallicity suggests that it has experienced a different evolutionary path from more metal-rich galaxies, like the Milky Way. This provides astronomers with a natural laboratory for studying the formation of stars and the interstellar medium in an environment that is chemically primitive compared to our own galaxy. The low metallicity of the LMC is thought to be the result of several factors, including its relative isolation from other galaxies and its smaller size. Since smaller galaxies tend to have lower metallicity, the LMC's lack of significant interactions with other galaxies over time has contributed to its chemical makeup. Additionally, the LMC's star formation history, which has been characterized by bursts of activity rather than continuous, steady star formation, has likely contributed to its lower metal content. The star-forming regions of the LMC, such as the Tarantula Nebula, are known to produce massive stars that burn through their fuel quickly, leaving behind a chemical imprint on the surrounding gas. Studying the chemical composition of the LMC offers valuable clues about the processes that lead to the enrichment of the interstellar medium. In galaxies with higher metallicity, the death of massive stars through supernova explosions injects heavy elements into the surrounding gas, enriching it and preparing it for the next generation of star formation. In galaxies with low metallicity like the LMC, the process of chemical enrichment is less advanced, and stars tend to form from gas that is relatively devoid of heavy elements. This makes the LMC a prime candidate for studying the early stages of galactic evolution and understanding how galaxies with low metallicity evolve into more chemically enriched systems. The fact that the LMC has been able to form a large number of massive stars despite its low metallicity is an intriguing mystery in itself. The stellar populations within the LMC, particularly the young, massive stars in regions like the Tarantula Nebula, provide evidence that star formation can still occur efficiently in metal-poor environments. This raises important questions about the factors that govern star formation and the conditions required for the birth of massive stars. Understanding these factors can provide valuable insights into the earliest stages of star formation in the universe, particularly in the context of the first generations of stars that formed in the aftermath of the Big Bang. While the Large Magellanic Cloud star-forming regions are some of its most well-known features, the galaxy is also home to a variety of other structures and phenomena that are of great interest to astronomers. One such phenomenon is the presence of multiple star clusters scattered throughout the LMC. These star clusters, which range in age from a few million years to several billion years, provide a wealth of information about the history of star formation in the galaxy. By studying the different ages and chemical compositions of these clusters, astronomers can trace the evolution of the LMC's star formation activity over time, gaining insights into the processes that drive the birth of stars and the growth of galaxies. The LMC also hosts a number of supernova remnants, which are the remnants of massive stars that have exploded in cataclysmic supernova events. These remnants, such as the N157b supernova remnant, are of particular interest because they provide valuable information about the types of supernovae that occur in low metallicity environments. Since supernovae play a key role in the chemical enrichment of galaxies, studying these remnants can help astronomers understand how heavy elements are distributed throughout the galaxy and how these elements contribute to the formation of new stars and planets. One of the most important aspects of the LMC is its interaction with its larger neighbor, the Milky Way. The gravitational pull of the Milky Way has had a profound impact on the LMC, shaping its structure and dynamics over billions of years. This interaction has led to the formation of tidal streams, such as the Large Magellanic Stream, which consists of gas stripped from the LMC by the Milky Way's gravity. The stream is a long, diffuse structure that extends over 200,000 light-years and provides crucial insights into the gravitational interactions between galaxies. The Large Magellanic Stream is thought to be the result of a past collision between the LMC and the Milky Way, and its study offers a glimpse into the processes that occur during galaxy mergers and interactions. By examining the structure of the stream and its composition, astronomers can learn more about the mechanics of tidal stripping and the effects of galaxy collisions on the formation and evolution of galaxies. The study of such interactions is important not only for understanding the history of the LMC but also for gaining a broader understanding of how galaxies evolve through their interactions with one another. The LMC's gravitational interactions with the Milky Way are also responsible for its current orbital path. The LMC is in a close, elliptical orbit around the Milky Way, and over time, this orbit has caused significant distortions in the LMC's shape and structure. These tidal forces have stretched and pulled the galaxy, leading to the irregular shape we observe today. The motion of the LMC through the gravitational field of the Milky Way has caused its stars and gas to move in complex patterns, providing valuable insights into the role of gravitational interactions in shaping the evolution of galaxies. The gravitational interactions between the Large Magellanic Cloud, LMC, and the Milky Way are not just responsible for the irregular shape of the LMC, they have also had profound effects on the overall dynamics of the galaxy. These interactions have influenced the movement of stars and gas within the LMC, driving complex processes of star formation, gas stripping, and the evolution of its structure over time. As the LMC continues to orbit the Milky Way, it will likely experience further tidal forces that will continue to reshape its morphology and star-forming activity. One of the most interesting consequences of the LMC's orbit is the impact it has on the star formation rates within the galaxy. The gravitational interactions with the Milky Way have led to periodic bursts of star formation within the LMC, often triggered by the compression of gas and dust as it moves through different regions of the galaxy's orbit. These bursts of star formation can be observed in the dense star-forming regions of the LMC, such as the Tarantula Nebula, which is one of the most active and massive star-forming regions known in the local group of galaxies. The Tarantula Nebula, or 30 Doradus, is located in the central region of the LMC and serves as a prime example of the LMC's intense star-forming activity. It is home to a large number of young, massive stars that are still in the process of forming from the surrounding gas and dust. The presence of these young stars provides a clear indication that the LMC is still undergoing significant star formation, despite its lower metallicity and the challenges it faces due to its interactions with the Milky Way. The study of regions like the Tarantula Nebula allows astronomers to understand the processes that govern the birth and evolution of massive stars in environments with low metal content. In addition to the star formation activity, the LMC is also home to a number of regions of active stellar death, including supernova remnants and areas of intense stellar wind. These phenomena contribute to the chemical enrichment of the galaxy, as the heavy elements produced by dying stars are expelled into the surrounding gas and dust. Over time, these elements are incorporated into new generations of stars, creating a cycle of stellar birth, death, and rebirth that is characteristic of many galaxies. The relatively low metallicity of the LMC, however, suggests that this cycle is not as advanced as it is in galaxies like the Milky Way, and studying the LMC offers a unique opportunity to explore the early stages of this process. The LMC's interactions with the Milky Way are also influencing its long-term future. Currently, the LMC is slowly moving toward the Milky Way and is expected to eventually collide with our galaxy in a few billion years. This collision will have a significant impact on both galaxies, potentially triggering a new wave of star formation as the two galaxies' gas clouds collide and interact. The gravitational forces involved in this collision could also result in the merger of the LMC and the Milky Way, leading to the formation of a new, larger galaxy. As the LMC moves closer to the Milky Way, it will also continue to interact with the Milky Way's satellite galaxies, such as the Small Magellanic Cloud, SMC. These interactions could further shape the structure and dynamics of the LMC, creating new tidal streams, gas flows, and bursts of star formation. The study of these interactions will provide important insights into the processes that occur during galaxy mergers and the eventual fate of the LMC as it merges with the Milky Way. In the broader context of the local group of galaxies, the Large Magellanic Cloud plays an important role in shaping our understanding of galaxy evolution and the processes that govern the formation and interaction of galaxies. As one of the most significant members of the local group, the LMC provides a unique opportunity to study a galaxy that is in the process of interacting with a larger, more massive galaxy. These interactions offer valuable clues about the ways in which galaxies evolve, both individually and through their interactions with other galaxies. The LMC's role in the larger cosmic picture is also of great interest to astronomers studying the formation of the universe itself. As one of the closest galaxies to the Milky Way, the LMC offers a unique window into the processes that took place during the early stages of galaxy formation. The galaxy's low metallicity, irregular shape, and complex history of star formation make it a key object of study for understanding how galaxies form and evolve in environments that are chemically and structurally different from our own. Additionally, the LMC's proximity to the Milky Way makes it an important laboratory for studying the influence of large-scale cosmic structures on the formation of galaxies. The Milky Way's gravitational pull has played a significant role in shaping the LMC, and studying this influence can provide insights into the way that larger galaxies affect the smaller galaxies around them. Understanding these interactions is crucial for developing a more complete picture of galaxy formation and evolution throughout the universe. Beyond its physical and structural characteristics, the LMC is also a key player in the search for dark matter. Like many other galaxies, the LMC exhibits a mysterious discrepancy between the amount of visible matter it contains and the gravitational effects observed within the galaxy. This discrepancy has led scientists to hypothesize the presence of dark matter, a form of matter that does not emit light or interact with electromagnetic radiation, but which exerts gravitational influence on visible matter. The study of the LMC's dark matter content can provide valuable clues about the nature of dark matter itself and help to refine our models of galaxy formation and dynamics. The presence of dark matter in the LMC is inferred from the motions of stars and gas within the galaxy. These motions indicate that there is significantly more mass present in the LMC than can be accounted for by the visible stars, gas, and dust. This missing mass is believed to be in the form of dark matter, which interacts with the visible matter through gravity but does not emit light. The study of dark matter in the LMC can provide valuable insights into its distribution, properties, and role in galaxy formation. One of the key challenges in studying dark matter in the LMC is the need for accurate measurements of the galaxy's mass distribution. Since dark matter does not interact with light, it cannot be directly observed, and its presence must be inferred from the effects it has on visible matter. By studying the motions of stars and gas in the LMC, astronomers can build models of the galaxy's mass distribution and estimate the amount of dark matter it contains. This research is important not only for understanding the LMC but also for gaining a deeper understanding of dark matter's role in the formation and evolution of galaxies across the universe. The LMC's complex history, its interactions with the Milky Way, and its potential as a key source of information about dark matter make it one of the most intriguing objects in the universe. Its proximity to our own galaxy allows us to study its various characteristics in unprecedented detail, providing a unique opportunity to explore the processes that govern galaxy formation, star formation, and the evolution of the universe itself. As we continue to study the LMC, it will undoubtedly remain a crucial piece of the puzzle in our quest to understand the cosmos and the forces that shape it. The Large Magellanic Cloud, LMC, continues to be a rich source of study for astronomers and astrophysicists alike, not only due to its proximity to the Milky Way but also because it holds important clues about the formation and evolution of galaxies. The ongoing research into the LMC's dynamics, star formation, and dark matter content offers new perspectives on a wide range of cosmic phenomena. As we deepen our understanding of the LMC, we learn more about the intricate processes that govern galaxies' development over time. One of the most remarkable features of the LMC is the Tarantula Nebula, a stellar nursery of unparalleled importance. The Tarantula Nebula, located in the LMC's central region, is the largest and most active star-forming region known within the local group of galaxies. Its vast size and immense star-forming activity make it an exceptional natural laboratory for astronomers studying the birth of stars, especially the formation of massive stars in environments with lower metallicity compared to the Milky Way. The nebula is home to some of the most massive stars ever observed, and studying this region helps astronomers understand the evolution of such stars and their ultimate fate. The Tarantula Nebula is a prime example of a stellar nursery, where the process of star formation is ongoing at an impressive rate. The region is filled with dense clouds of gas and dust, which collapse under their own gravity to form new stars. Some of these stars are so massive that they can emit tremendous amounts of radiation, which in turn can affect the surrounding gas, causing it to glow brightly. The intense radiation from these stars can also drive strong stellar winds, further shaping the surrounding nebula and influencing the formation of new stars. What makes the Tarantula Nebula particularly fascinating is its relatively low metallicity. The LMC, as a whole, has a lower abundance of heavy elements compared to the Milky Way, and the Tarantula Nebula is no exception. This low metallicity offers a rare opportunity for astronomers to study star formation in a primordial environment, similar to conditions that may have existed in the early universe. By studying this region, scientists can learn more about how stars formed during the early stages of the cosmos, before the abundance of heavy elements became more widespread. Moreover, the presence of several massive, short-lived stars in the Tarantula Nebula offers valuable insights into the life cycles of the most extreme types of stars. These stars are often only around a few million years old, but their explosive deaths in supernovae will ultimately enrich the surrounding gas with heavy elements, contributing to the next generation of star formation. The study of these stars provides essential information on how elements like carbon, oxygen, and iron are synthesized in the cores of massive stars and distributed throughout the galaxy. In addition to the Tarantula Nebula, the LMC also contains a number of other regions of star formation, each contributing to the galaxy's overall stellar population. The LMC's star-forming activity is not limited to a single region but is spread across the galaxy, with several smaller nebulae and molecular clouds scattered throughout its disk. These regions are critical for understanding the complex relationship between gas, dust, and star formation in low metallicity environments. While the LMC's star formation rates are fascinating, its interactions with the Milky Way provide even more intriguing possibilities for future research. As the LMC orbits around the Milky Way, it is continually influenced by the gravitational forces of our galaxy. These forces can trigger bursts of star formation as gas clouds are compressed or stretched by tidal interactions. Some of these interactions may even lead to the disruption of gas clouds, preventing them from forming stars or leading to the formation of new stars in unexpected locations. In the past, the LMC's interactions with the Milky Way have likely been responsible for the creation of several tidal structures, such as stellar streams and tidal tails, which can be observed as faint streams of stars extending far from the main body of the galaxy. These structures provide direct evidence of the LMC's dynamic history and give astronomers important clues about the forces that have shaped its evolution. The study of these tidal features helps scientists understand the gravitational interactions that occur during galaxy encounters and provides a deeper understanding of how galaxies evolve over time. The gravitational interactions between the LMC and the Milky Way have also influenced the overall morphology of the LMC. Unlike the more orderly, spiral structure of the Milky Way, the LMC is an irregular galaxy with a highly asymmetric shape. The tidal forces exerted by the Milky Way have likely played a significant role in shaping the LMC's unusual appearance. By studying the LMC's structure and the effects of these interactions, astronomers can gain insights into the processes that drive the evolution of irregular galaxies and how these galaxies may evolve into more structured forms over time. One of the key aspects of the LMC's interaction with the Milky Way is the fact that it is part of a complex system of satellite galaxies that orbit around our galaxy. The LMC and its smaller companion, the Small Magellanic Cloud, SMC, are often referred to as the Magellanic Clouds, and together they form one of the most important satellite systems in the local group. The gravitational interactions between the LMC, the SMC, and the Milky Way are responsible for a variety of interesting phenomena, including the formation of tidal tails, the distortion of the LMC's shape, and the exchange of gas and stars between the galaxies. Over the next few billion years, the LMC is expected to continue its orbit around the Milky Way and will eventually collide with our galaxy. This collision will have profound effects on both galaxies, potentially triggering a new wave of star formation as the gas clouds from the two galaxies collide. The interaction could also result in the merger of the two galaxies, creating a new, larger galaxy. The study of the LMC's future collision with the Milky Way offers important insights into the processes that occur during galaxy mergers and provides a glimpse into the distant future of our own galaxy. As we look further into the future, the ultimate fate of the LMC and its interactions with the Milky Way will provide valuable clues about the long-term evolution of galaxies. The collision between the LMC and the Milky Way will likely play a role in reshaping both galaxies, creating a new, more massive galaxy with an altered structure and star formation history. Understanding these processes is crucial for astronomers as they seek to unravel the mysteries of galaxy formation and evolution across the cosmos. The Large Magellanic Cloud is a key object of study in the field of galaxy evolution, providing valuable insights into the processes that shape galaxies over time. Its unique combination of low metallicity, intense star formation, and complex interactions with the Milky Way make it an essential laboratory for understanding the history of galaxies and the forces that govern their development. As we continue to study the LMC, we will undoubtedly uncover new details about the evolution of galaxies, the birth and death of stars, and the nature of dark matter, further enriching our understanding of the universe itself. The Large Magellanic Cloud remains one of the most fascinating objects in the universe. From its active star-forming regions, such as the Tarantula Nebula, to its complex interactions with the Milky Way, the LMC offers a wealth of information about the processes that shape galaxies. Whether studying its gravitational interactions with the Milky Way, its low metallicity, or its role in the formation of massive stars, the LMC continues to captivate astronomers and inspire new research into the fundamental workings of the cosmos. As we continue to explore this remarkable galaxy, we gain a deeper understanding of the vast and mysterious universe we inhabit. The Large Magellanic Cloud is not merely a stellar playground, it is a living chronicle of cosmic history, stitched together by billions of years of gravitational entanglements, ancient starbursts, chemical evolution, and celestial motion. Every observation made of the LMC, whether by ground-based telescopes or space observatories, contributes a data point to this grand, sprawling narrative. As one of the closest extragalactic systems to the Milky Way, it acts as a kind of interstellar mirror, both familiar and alien, reflecting what once was, what is, and what may yet become of galaxies like our own. Let us now dive deeper into the dynamical structure of the LMC. While classified as a barred irregular galaxy, the Large Magellanic Cloud shows certain traits commonly associated with spiral galaxies. It has a one-armed spiral structure, an unusual trait. Most spiral galaxies have two or more well-defined arms, but the LMC has one dominant spiral arm winding out from its central bar. This feature hints at a once more organized past, possibly disrupted by repeated gravitational skirmishes with the Milky Way and the small Magellanic Cloud. This disruption has warped the disk of the LMC, creating a shape that is simultaneously symmetrical and lopsided. The disk itself is tilted with respect to our line of sight, giving astronomers a unique vantage point from which to measure three-dimensional motions of stars and gas within the LMC. This inclination allows researchers to model its internal rotation and probe its mass distribution in exceptional detail. And it's through this analysis of stellar motions that we arrive at one of the LMC's most mysterious features: the possible presence of dark matter. Dark matter, which neither emits nor absorbs light, is detectable only through its gravitational influence on visible matter. By examining how stars orbit within the LMC, scientists can estimate the galaxy's total mass and compare it to the mass inferred from its visible stars and gas. The discrepancy between these two values points directly to dark matter. In fact, the LMC may contain a substantial halo of dark matter that not only governs its internal dynamics but also influences its interactions with the Milky Way. The importance of the LMC's dark matter content extends beyond academic curiosity. It plays a crucial role in the galaxy's gravitational effect on the Milky Way. Recent studies suggest that the LMC, despite its relatively small size compared to the Milky Way, has a surprisingly large gravitational footprint. Its motion through the Milky Way's halo creates a wake, a ripple in our galaxy's dark matter distribution. This wake can perturb the orbits of stars in the Milky Way, particularly those in its stellar halo, providing astronomers with indirect clues about the invisible dark matter that surrounds both galaxies. In fact, the gravitational wake of the LMC has already been observed. Using data from the Gaia Space Observatory, astronomers have detected distortions in the Milky Way's stellar halo that are consistent with the gravitational influence of the LMC's passage. These observations not only confirm the LMC's massive dark matter halo but also help refine our understanding of how satellite galaxies can shape and sculpt their hosts through invisible but profound means. Beyond the gravitational and structural intricacies of the LMC lies a rich tapestry of stellar populations, each offering a snapshot of different epochs in the galaxy's long life. The LMC contains ancient stars that formed more than 10 billion years ago, alongside newborn stars that have emerged within the last few million years. This broad stellar age range allows astronomers to reconstruct the LMC's star formation history in exquisite detail. One particularly useful tool in this endeavor is the analysis of stellar clusters. The LMC is home to numerous globular and open clusters, which act as time capsules, groups of stars that formed at the same time and from the same material. By studying these clusters, researchers can pinpoint when major bursts of star formation occurred and correlate them with possible interactions or mergers. Interestingly, the LMC's star formation history is punctuated by periodic surges, often coinciding with close encounters with the SMC or the Milky Way. These bursts are visible in both stellar clusters and field stars, revealing that gravitational interactions can act as triggers for galaxy-wide transformations. This process, known as tidal triggering, demonstrates how external forces can reignite star formation in a galaxy that may otherwise be evolving passively. In addition to traditional stars and clusters, the LMC hosts several types of exotic objects that illuminate the later stages of stellar evolution. For example, it contains numerous planetary nebulae, the glowing shells of gas ejected by dying stars, as well as white dwarfs, neutron stars, and even black holes. These remnants tell the story of stellar death in environments that differ markedly from those of the Milky Way. Their chemical compositions, light curves, and behavior provide important data on how metallicity influences stellar lifespans and deaths. Among the most fascinating of these stellar remnants are the supernova remnants scattered throughout the LMC. These expanding shockwaves mark the violent deaths of massive stars and act as beacons of recent star formation. One of the most famous supernova remnants in the LMC is SN 1987A, the brightest supernova visible from Earth in over 4 centuries. Discovered in 1987, this event gave astronomers a front-row seat to the death of a massive star and offered unprecedented insight into the physics of core-collapse supernovae. SN 1987A was particularly valuable because it was observed across the entire electromagnetic spectrum, from radio waves to gamma rays. For the first time, neutrinos from a supernova were detected, confirming theoretical predictions about what happens inside a collapsing star. The aftermath of SN 1987A continues to be studied, as its shockwave interacts with surrounding material, providing a slow-motion view of how such explosions shape the interstellar medium. Furthermore, the LMC's proximity allows astronomers to study its variable stars in exceptional detail. These stars, such as Cepheid variables and RR Lyrae stars, change brightness in a predictable manner and serve as standard candles for measuring cosmic distances. The LMC has long been used as a calibration point for the extragalactic distance scale. By determining the precise distances to variable stars in the LMC, scientists can refine the measurements of far more distant galaxies, improving our understanding of the scale and expansion rate of the universe itself. The use of Cepheid variables in the LMC was instrumental in confirming that the universe is expanding. In fact, it was by studying such variables in the Magellanic Clouds that Edwin Hubble first realized that galaxies lie beyond the Milky Way, thereby revolutionizing our understanding of the cosmos. To this day, the LMC plays a central role in calibrating the Hubble constant, a measure of the universe's rate of expansion. Adding to the complexity of the LMC's celestial portrait is its relationship with the Small Magellanic Cloud. Though smaller and more irregular, the SMC is gravitationally bound to the LMC, and the two galaxies are connected by a bridge of gas and stars. This bridge, known as the Magellanic Bridge, is a testament to the ongoing gravitational interactions between these galaxies. Astronomers believe the Magellanic Bridge formed during a close encounter between the LMC and SMC around 200 million years ago. The bridge contains young stars, indicating that star formation has occurred within the stream of stripped gas connecting the galaxies. The presence of such structures underscores how galaxy interactions are not only destructive but also creative, capable of sparking new generations of stars in the very material torn away by gravitational forces. Meanwhile, trailing behind the LMC and SMC is the vast and enigmatic Magellanic Stream, a ribbon of neutral hydrogen gas that stretches across a significant portion of the sky. The stream is thought to be the result of gas being stripped from the LMC and SMC by the gravitational and hydrodynamic effects of their interactions with the Milky Way. The study of the Magellanic Stream offers clues about the past orbits of the clouds and the influence of the Milky Way's hot halo gas. The existence of the stream also points to another key mystery. Why do the LMC and SMC still retain so much gas? Most satellite galaxies of the Milky Way are gas-poor, having lost their reservoirs to ram pressure stripping or tidal forces. Yet the LMC and SMC remain gas-rich and actively forming stars. This suggests either that they are on their first infall into the Milky Way's gravitational field or that they possess unusually deep potential wells, possibly due to their substantial dark matter halos. This mystery deepens when considering simulations of galaxy formation in a cosmological context. Many simulations predict that satellite galaxies like the LMC should lose their gas relatively quickly after entering a larger galaxy's halo. The persistence of star formation in the LMC and its rich interstellar medium challenge these models and offer opportunities to refine our understanding of galactic evolution on small scales. The puzzle of the Large Magellanic Cloud's persistent gas richness, particularly its abundance of cold molecular gas, has spurred a wide range of astrophysical research. One hypothesis is that the LMC has experienced repeated episodes of gas accretion from the intergalactic medium, or even from its interactions with the SMC. The gravitational interplay between the two clouds may create tidal flows that move gas back and forth, temporarily replenishing star-forming reservoirs and delaying the quenching processes observed in many other satellite galaxies. Furthermore, there is evidence to suggest that the LMC has a unique ability to retain its gas due to its compact structure and relatively strong gravitational binding. Unlike many other dwarf galaxies, the LMC's gravitational potential well is deep enough to prevent stellar winds and supernova explosions from expelling all of its gas. This self-regulating mechanism allows the galaxy to maintain a delicate equilibrium between gas loss and gas retention, thereby supporting ongoing star formation for billions of years. This constant interplay between gravity and gas is most vividly captured in the LMC's complex interstellar medium, ISM. The ISM in the LMC comprises multiple phases: cold molecular clouds, warm ionized gas, hot X-ray emitting plasma, and vast dust lanes. Each of these phases plays a distinct role in the life cycle of stars. Molecular clouds act as stellar nurseries, birthing new generations of stars. These stars, in turn, inject energy back into the ISM through radiation, stellar winds, and eventually supernovae, reshaping the surrounding environment and setting the stage for the next cycle of star formation. One region where this cycle is especially prominent is the Tarantula Nebula, also known as 30 Doradus. This colossal star-forming complex is not just the most active region in the LMC, it's the most vigorous stellar nursery in the entire local group of galaxies. Spanning over 1,000 light-years, the Tarantula Nebula is a turbulent cauldron of ionized gas, massive stars, and dense molecular clouds. Within it lies the massive star cluster R136, which contains some of the most massive stars ever observed, including several exceeding 100 solar masses. The sheer scale and intensity of star formation in the Tarantula Nebula make it a laboratory for studying the processes that shape giant star clusters. These clusters may be the modern analogues of the globular clusters that formed in the early universe. By observing their formation and evolution in the LMC, astronomers hope to unlock the secrets of how the earliest generations of stars came into being. But the LMC's contribution to astrophysics goes far beyond star formation. It serves as a proving ground for cosmological models, stellar population synthesis, and even the physics of dust grains. The dust in the LMC differs significantly from that in the Milky Way, both in composition and in how it absorbs and scatters light. Understanding these differences helps refine models of light extinction and reddening, which are crucial for accurately measuring the properties of distant galaxies. Moreover, the LMC's relatively low metallicity, meaning a lower abundance of elements heavier than helium, makes it a valuable analog for studying early galaxies. In the early universe, most galaxies had low metallicity because heavy elements are produced over time through stellar nucleosynthesis. The LMC, therefore, offers a nearby example of what galaxies might have looked like during the epoch of galaxy formation. This low metallicity also influences the types of stars that form in the LMC. For instance, massive stars in low metallicity environments tend to lose less mass over their lifetimes due to weaker stellar winds. This has significant implications for their evolution and the types of supernovae they produce. Some of these massive stars may collapse directly into black holes without a supernova explosion, a process that could help explain the origins of some black holes detected through gravitational waves. Indeed, the LMC's environment has become a testbed for gravitational wave astronomy. As instruments like LIGO and Virgo detect more black hole and neutron star mergers, researchers are increasingly interested in where these mergers occur. The LMC, with its active star formation and dense stellar environments, could host such progenitor systems. Identifying and modeling these environments in nearby galaxies helps to interpret the signals we receive from the distant universe. Adding further intrigue is the LMC's motion through space. Traveling at a velocity of over 300 km per second relative to the Milky Way, the LMC is not simply orbiting our galaxy. It may actually be on a first-in-fall trajectory. If this is true, it would radically alter how we understand the evolution of satellite systems and the growth of galactic halos. The idea of a first-in-fall is supported by its large proper motion, measured with exquisite precision by the Hubble Space Telescope and Gaia. This first-in-fall scenario has profound consequences. It suggests that the LMC hasn't yet had time to undergo significant tidal stripping, which explains why it still contains so much gas and is still forming stars at a prodigious rate. It also implies that its influence on the Milky Way's disk, halo, and even dark matter distribution is still in the early stages. Over the next few billion years, the gravitational interaction between the LMC and the Milky Way could dramatically reshape both galaxies. Eventually, the LMC may merge with the Milky Way. Simulations show that this merger will not be a violent collision like those between two spiral galaxies of equal mass, but rather a more gradual assimilation. However, the consequences will still be dramatic. The LMC's mass, potentially as high as 1/4 of the Milky Way's dark matter halo, will significantly perturb the Milky Way's structure. The disk may warp, star formation rates could increase, and stellar streams might be created as the LMC's stars are spread throughout our galaxy. These long-term interactions are not limited to gravitational effects. They also include the mixing of stellar populations and chemical elements. As the LMC merges with the Milky Way, its stars, many of which are metal-poor, will enrich the galactic halo and provide insights into the assembly history of our galaxy. In essence, the LMC will become part of the Milky Way's fossil record, a galactic relic absorbed into the grand tapestry of our cosmic home. Beyond the immediate science, the LMC also holds cultural and historical significance. It has been known to humanity for millennia, visible as a hazy patch in the southern sky. Ancient indigenous cultures in the southern hemisphere incorporated it into their cosmologies, while early European navigators used it for celestial navigation. Its role in human history reminds us that the study of the cosmos is not merely a scientific pursuit, it is also a deeply human endeavor, bridging cultures, centuries, and civilizations. Today, the LMC continues to inspire new generations of astronomers, astrophysicists, and stargazers. It is the subject of countless observations, from Earth-based telescopes like the Very Large Telescope in Chile to space-based missions such as the Hubble Space Telescope, Spitzer, and the James Webb Space Telescope. Each new dataset adds a layer of complexity to our understanding of this remarkable galaxy, and each new discovery opens the door to fresh questions. One area of emerging research is the search for exoplanets within the LMC. While most exoplanet studies focus on stars within the Milky Way, the detection of planets in the LMC would represent a significant leap forward in our understanding of planetary formation across different galactic environments. Microlensing surveys such as OGLE, Optical Gravitational Lensing Experiment, and MOA, microlensing observations in astrophysics, have the potential to detect such distant worlds, albeit rarely and with great difficulty. If planets can indeed form and persist in galaxies like the LMC, it raises tantalizing possibilities about the universality of planetary systems. Could there be habitable worlds orbiting stars in the LMC? Could life, however simple or exotic, have taken root in this neighboring galaxy? These questions remain speculative for now, but they capture the imagination and drive future exploration. The prospect of habitable worlds within the Large Magellanic Cloud, while currently theoretical, carries profound implications for our understanding of life's potential distribution across the universe. The LMC, though distinct from our own Milky Way in many ways, contains billions of stars, each with the potential to host planetary systems. If even a small fraction of those stars possess planets within habitable zones, the statistical likelihood of life elsewhere, even in a neighboring galaxy, becomes more compelling. But determining habitability is complex. The stars in the LMC are generally younger, and the galaxy's lower metallicity may influence the formation of rocky planets. In metal-poor environments, gas giants may be more common than terrestrial worlds, and the formation of Earth-like planets may be rarer. Yet this doesn't entirely preclude habitability. Recent discoveries in exoplanet research have shown that even gas giants can host potentially habitable moons, and planetary formation models are constantly evolving to accommodate new findings. If moons can sustain atmospheres, magnetospheres, and liquid water, then life, microbial or complex, may not be exclusive to Earth-like planets. Adding further intrigue to the LMC's structure is its apparent asymmetry. It's not a perfectly round or uniformly distributed galaxy. Its disk appears warped, possibly due to its gravitational interaction with the small Magellanic Cloud, or even the Milky Way itself. These warps suggest a long history of tidal encounters that have reshaped the galaxy's morphology. Unlike the relatively smooth spiral arms of larger galaxies, the LMC's disk shows signs of ongoing dynamism and external influence. This morphology gives researchers a vivid canvas to study the real-time effects of galactic interaction. Another fascinating aspect is the LMC's magnetic field. Though weak compared to Earth's, the magnetic field in the LMC is surprisingly coherent across large scales. This coherence challenges traditional models of how galactic magnetic fields evolve, especially in dwarf galaxies. Understanding the origin and maintenance of such magnetic fields could have significant ramifications for our comprehension of cosmic ray propagation, star formation dynamics, and even the large-scale structure of the universe. Meanwhile, its proximity to Earth makes the LMC a key target for mapping the cosmic distance ladder. Because the LMC is relatively close and filled with variable stars like Cepheids and RR Lyrae, it provides an essential anchor for calibrating distances to far-off galaxies. These calibrations underpin measurements of the Hubble constant, the rate of expansion of the universe. Discrepancies in the Hubble constant derived from different methods have led to a major tension in cosmology, known as the Hubble tension. The LMC plays a starring role in trying to resolve this issue. Precision measurements of distance to the LMC, aided by instruments like Gaia and the Hubble Space Telescope, have narrowed uncertainties to within a few percent. These measurements, when cross-referenced with Type I supernovae and redshift data, feed directly into calculations about the age, size, and fate of the universe. In a very real sense, our ability to understand cosmic expansion depends on how well we understand a neighboring dwarf galaxy. This makes the LMC not only a neighbor in space but a cornerstone of cosmic comprehension. It acts as a scale reference for astrophysical quantities ranging from the life cycles of stars to the acceleration of the universe. The LMC provides a benchmark for everything from the calibration of standard candles to the modeling of galactic evolution. As we continue to observe it across all wavelengths, from radio and infrared to X-ray and gamma ray, we uncover more layers of complexity. Infrared surveys penetrate its dust, revealing hidden star-forming regions. Radio telescopes map the distribution of hydrogen gas, tracing the structural skeleton of the galaxy. High-energy observatories detect remnants of stellar explosions and the emissions from exotic objects like pulsars and black holes. One particularly notable remnant is the aftermath of SN 1987A, a supernova that exploded in the LMC in 1987. It was the closest supernova observed in modern times, offering unprecedented insight into stellar death. The detection of neutrinos from this event marked a historic milestone in particle astrophysics, linking stellar events to subatomic physics. To this day, SN 1987A remains a case study in supernova modeling, as astronomers watch the evolving nebula and analyze the elements produced in the explosion. This explosion, and others like it, underscore the LMC's importance as a site for studying cosmic alchemy. Supernovae forge the elements that form planets, bodies, and ultimately life. By understanding the rates and types of supernovae in the LMC, we gain insight into how the periodic table was built over cosmic time. Moreover, the LMC contains numerous X-ray binaries, where a compact object, such as a neutron star or black hole, orbits a normal star and pulls matter from it. These exotic systems are key sources of X-rays and laboratories for studying the physics of accretion, relativistic jets, and magnetic fields. Because the LMC is relatively nearby, these systems can be studied in exquisite detail, allowing scientists to test the predictions of general relativity and accretion theory. In addition to isolated stars and binaries, the LMC also hosts massive star clusters, both young and old. Some of the younger clusters contain stars just a few million years old, still embedded in their natal clouds. Older clusters, such as NGC 1866 and NGC 1835, span the age range from a few hundred million to over 10 billion years. This wide distribution allows researchers to track stellar evolution over time, comparing how stars of different masses, metallicities, and ages behave. The presence of globular clusters in the LMC also raises intriguing questions about their formation. Did these clusters form in situ within the LMC, or were they captured from smaller galaxies during earlier mergers? Studying their orbits, compositions, and spatial distributions may yield answers about the assembly history of the LMC, and by extension, about the broader mechanisms of galactic growth through hierarchical merging. On a broader scale, the LMC is part of the Magellanic System, a larger structure that includes the Small Magellanic Cloud, the Magellanic Bridge, and the Magellanic Stream. These features trace the gravitational and hydrodynamic interactions between the clouds and the Milky Way. The Magellanic Bridge is a stream of gas and stars connecting the LMC and SMC, thought to have formed from tidal stripping during a past close encounter. The Magellanic Stream, on the other hand, is a vast trail of gas extending across more than 200 degrees of the sky, slowly being accreted by the Milky Way. These structures are not only visually spectacular, they are scientifically rich. The stream contains information about the chemical composition of the Magellanic Clouds, the dynamics of gas in the circumgalactic medium, and the processes by which galaxies grow by accreting smaller companions. Mapping the density, velocity, and composition of these streams helps model the evolution of galactic halos and the inflow of cold gas into massive galaxies. Furthermore, the LMC's orbit and proper motion suggest it may have once been part of a small group of galaxies, a Magellanic group, that fell into the Milky Way together. If this is true, it reinforces the idea that galaxy clusters grow not by solitary additions but by group accretion. In this model, the LMC brings with it a legacy of smaller companions, some of which may now be satellites of the LMC rather than the Milky Way directly. Identifying and characterizing these satellites remains a work in progress, but the evidence is mounting. The discovery of ultra-faint dwarf galaxies near the LMC suggests a hierarchical structure within a hierarchical structure. These faint systems challenge detection limits and are key to resolving discrepancies between simulations and observations, what astronomers call the missing satellite problem. As research continues, the LMC's role expands from being just a satellite galaxy to being a microcosm of cosmic evolution. It is a dynamic laboratory, a remnant of the early universe, a builder of elements, a host of strange phenomena, and a witness to the drama of galactic interaction. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.